Hello,
Hello, hello.
how are you?
Hello. Hello. Dr. Anjali, can you hear me?
Yes, sir.
I think we can start the program.
Okay, sir.
Wait a second.
Okay. We led the industrial revolution and white revolution. Now it's time for a revolution in disaster resilient infrastructures. With his words of Honorable Prime Minister Shri Narendra Modi, I would like to extend my warm welcome to one and all. Respected Chief Guest of the Day, Shri Vivek Chandelji, Director, Technical Education, Vocational and Industrial Training, Government of Himachal Pradesh, Professor Dr. P.L. Sharma, Director, University Institute of Technology, Himachal Pradesh University, Coordinator of this faculty program, Dr. Mahesh Sharma, and participants of this faculty development program from engineering organizations and industries who have joined us through virtual link. A very good morning to one and all. On behalf of University Institute of Technology, Himachal Pradesh University, myself Dr. Anshi Sharma, and it gives me immense pleasure to stand on this threshold and to welcome you all in this online AICTE sponsored faculty development program on disaster resilient infrastructure. Although life has thrown an interesting curveball at us with the coronavirus pandemic, but it has also shown us way to use technology in a different way and to participate in group activities held at distance. So, amid this pandemic, let's pray for good health and prosperity. Now, with the permission of respected chief guest of the day and Director, University Institute of Technology, Himachal Pradesh University, I would like to take this opportunity to officially start this program by virtually raising the curtain and by playing the Saraswati Vandana thereafter. May I, sir?
करो start करो.
Am I audible, sir?
Yes, you are audible, ma'am.
Okay, sir.
Dr. Anjali, can you hear me? द्वारा से कट जी सर, क्या नाम है सर? Dr. Anjali, can you hear me? I think we had some problem with the internet. Nevertheless, can you hear me, Dr. Anjali? So we can move ahead with our program. So
Okay.
good morning, everyone. I think we had a little internet glitch.
Yes, sir. Actually, I was not able to unmute myself.
It's
So sorry
okay.
from my side.
Yeah, it's
Yeah.
okay, Dr. Anjali. I can fully understand, and a very warm good morning to every one of you. First of all, sorry for the glitch because we all are connected through internet, and this institute is somewhere in the Himalayas, so we face lot of internet disconnectivity many times. Nevertheless, I would like again to welcome all of you in this program. Myself, Dr. Mahesh Sharma, the coordinator of this program. So again, I extremely apologize for a little internet glitch, but we'll try to take care of it in the near future. So let us start. A brief introduction about the university, so that all of you, we were presuming that you will be here in offline mode. That would have been wonderful to host you in the beautiful campus of Himachal Pradesh University. So a brief overview of this university, which was established in 1970 as an autonomous body. It is located in the picturesque city of Shimla, which is very popular for among tourists throughout the world. The university is having around 8 institutes, 9 regional centers, and approximately 50 departments, which has around 400 faculty members, and around 8,000 students are presently enrolled in the university in various programs. The university has affiliations from UGC, NAC, AIU, etc. My institute, that is University Institute of Technology, was established in 2000. It is the engineering wing of Himachal Pradesh University. Recently, we have started 6 departments in the field of computer science engineering, information technology, electrical engineering, electronics and communication engineering, and applied science and humanities. My department, that is Department of Civil Engineering, was established in the year 2021 It's a very young department, I must say that. And so it's a proud moment for my department and my institute that we are hosting this AICTE sponsored faculty development program on disaster resilient infrastructure. And about the program, so the idea was given by our respected director that this department, which is being set up in Himachal Pradesh University, needs to cater to the demands of the hilly regions of the state and country. So that was the prime idea that came. And so we thought of organizing this program by taking into consideration that how we can upgrade the teaching, training, and research skills of teachers, research scholars, with the recent development in geotechnical earthquake engineering, mainly in disaster resilient infrastructure. So you might have gone through the schedule and our speakers. We have tried to bring together the elite speakers throughout the world. They are from IIT, NIT, CSIR, CBR, and Roorkee, and various speakers from USA, Australia, Italy, and Britain. And we also, besides organizing a technical program, our director wanted that there should be a little tinge of spirituality, how spirituality can help academia. So we have contacted renowned Shri M, a Padam Bhushan awardee, to take a lecture on spirituality and how a spirituality can play a significant role in academia. So with these words, I think you might have gone through the course content of this program. The course content includes geotechnical earthquake engineering, landslide disaster mitigation, reinforced soil structures, sustainable disaster resilient structures, railway infrastructure development, and unsettled soil mechanics. So the idea is basically to bring together the topics which are relevant to my state in this rainy season where we are every day countering so many landslides and slow failures leading to a huge number of casualties. So that was the crux of this program. I hope that we'll be able to perform up to the mark and under the guidance of Director UIT. So now I hand over again back to Dr. Anjali, who is the moderator of today's program. Dr. Anjali, you please carry on. Thank you.
Thank you, sir. And now, on the occasion of inaugural ceremony of this faculty development program, now I request Professor Dr. P.L. Sharma, Director, University Institute of Technology, Himachal Pradesh University, to address and welcome respected chief guests, all dignitaries and participants of this faculty development program. Also, I request coordinator to unmute Director, sir, please. Director, sir.
Okay. Am I audible, Dr.
Yes,
Anjali?
Yes, sir, you are audible, sir.
Yes, okay. Worthy chief guest of this faculty development program, Sri Vivek Chandel, Director Technical Education, Government of Himachal Pradesh, and Dr. Shantanu Sarkar, Chief Scientist and Head CSIR CBRI Roorkee, who is going to deliver his talk after this inaugural function. Dr. Mahesh Sharma, coordinator of this program, Dr. Anjali, Dr. Neeru, Dr. Shyam, and faculty members of UIT and dear participants. It gives me immense pleasure that Sri Vivek Chandel, Director Technical Education, Government of Himachal Pradesh, is with us on this very occasion of inaugural function. On this occasion, I welcome Shri Vivek Chandel, and also I welcome Dr. Shantanu Sarkar, who is ready to deliver his talk after this function. And I can say that Dr. Mahesh is taking keen interest to organize all such type of activities in the UIT, and also he is very keen in the growth of UIT as well as the growth of the department, civil department. Uh, 2 or 3 days back, I requested Shri Vivek Chandel. He has a very hectic schedule, and right now he is in Chandigarh also with some assignment of the state government. But even though he said, "Okay, sir, I will be there with you on this function," so it is a greatness of Shri Vivek Chandel, who is having with us on this very occasion. The speakers for this program are also of high profile, and they are from prestigious institute. Some of them are from abroad, and I hope all the participants who are joining this program, they will get benefited from this program. This program is related with disaster management, and disaster management is controlled by the civil engineer. And whatsoever we do in our life, that may be institute, that may be any building, construction of any building, first we have the need of civil engineer. Civil engineers take the lead, then we have to contact to the electrical engineer, then electronics and communication engineer, then computer science engineer, in this hierarchy. But first requirement is of a civil engineer. So the department of UIT, civil engineer department, is leading in all the areas. And I would say congratulations to the Dr. Mahesh and his entire team, as well the faculty members of this civil department. They are taking initiative to do this thing. And also I would like to thank Dr. R.K. Sone, who is the head of this ATAL program, AICTE New Delhi, who have assigned this program to the UIT to organize this program in the civil department. And once again, I would like to thank Shri Vivek Chandel to be here with us on this very occasion as a chief guest. Thank you, Vivek Chandel. Thank you. Jai Hind, Jai Himachal.
Thank you, sir. I am profusely elated to take an opportunity to welcome our chief guest of the day, Shri Vivek Chandel ji. On behalf of Himachal Pradesh University, I thank you, sir, for providing your virtual presence in the inaugural ceremony of this faculty development program. So once again, I would like to take permission from the respected chief guest to officially inaugurate this program, and by virtual raising the curtains and by playing the Saraswati Vangna thereafter. So once again, I request respected chief guest to raise the curtain.
तुषारहारधवला या शुभ्रवस्त्रावृता या वीणावरदण्डमण्डितकरा या श्वेतपद्मासना या ब्रह्माच्युतशङ्करप्रभृतिभिः देवैः सदा वन्दिता सा मां पातु सरस्वती भगवती निःशेषजाड्यापहा शुक्लां ब्रह्मविचारसारपरमा आद्यां जगद्व्यापिनीं वीणापुस्तकधारिणीम् अभयदां जाड्यान्धकारापहा हस्ते स्फाटिकमालिकां विदधतीं पद्मासने संस्थितां वन्दे तां परमेश्वरीं भगवतीं बुद्धिप्रदां शारदाम्।
Thank you, sir. Shri Vivek Chandel ji is a topper of Himachal Pradesh Administrative Services of 2004 batch. He had worked as administrative officer in almost all districts of Himachal Pradesh. Presently posted at Director Technical Education, Vocational and Industrial Training, Government of Himachal Pradesh. Apart from this, he is member of Board of Governors of NIT Hamirpur, Triple IT Una, IIM Sirmaur, and Vice Chairman of HP Techniki Shiksha Board, Dharamshala. With these words, I request respected Chief Guest of the Day, Shri Vivek Chandel ji, to go on the ceremony of this Faculty Development Program. Respected sir. Also, I request coordinator to mute respected Chief Guest.
Thank you so much, Dr. Anjali. First, I would like to thank Dr. P.L. Sharma ji, who has not only remained my guide, in fact, he taught me mathematics when I was in Bilaspur. So it's my honor and privilege to be here amongst all of you august personalities. And during my introduction, the important part and underlying part, you did not mention that I have also remained student of this August University. I've spent my 5 years in HP University, did my MBA and LLB from Himachal University only. So I once again thank Dr. P.L. Sharma ji, who has given me this opportunity, and it's really an honor to be invited as chief guest in any of the programs in your alma mater. So I've been to many programs, many universities, but it's a real honor for me. Down the line, if I think of my years in university, I got admitted in the year 1997. Then till 2002, I was there. I've studied in Everlodge Boys Hostel, and HP University has contributed a lot in making of my personality. Whatever small being I am today, I owe it to HP University and my teachers like Dr. P.L. Sharma. Now, coming to the topic, disaster resilient infrastructure. So before I dwell on the topic, I would like to inform all the participants that I've been being in the administration, I've been associated with the disaster mitigation, disaster management since long. So I have had the opportunity to dwell into many of the topics and visited many of the areas which were devastated by the earthquakes. So before we come to the other points, first I would like to share my few of the experiences. In the year 2016, we got the opportunity to visit Nepal. In fact, it was in December 2017. We got the opportunity to visit Nepal, where in 2015, probably the date was 25th of April, it was struck by a huge earthquake. And the epicenter was in Gorkha district, which is Gorkha district. It is in the central Nepal, in fact. And I had the opportunity to go to the place called Barpat, which was its epicenter. So I had the opportunity to see the practices which they are adopting, which they are using for future preparedness and making resilient infrastructure there. And if we talk of Himachal, who else would know the importance of this more than us? We have had devastating earthquake way back in the year 1905, 1905 to be precise. It was 4th of April 1905 when we had this a big disaster in our entire area. Coming from there till today, we have come a long way in our preparedness. If I talk of Himachal, in Himachal Pradesh, many activities are being undertaken today. We have HPSDMA, Himachal Pradesh State Disaster Management Authority, and then we have district disaster management authorities all over our 12 districts, wherein Deputy Commissioner is the chairman of the authority and important functionaries are its members there. So HPSDMA is undertaking many activities. I would just mention 2-3 of them, since it is an inaugural function today, inaugural activity. We are sitting here, would dwell some other day on in detail. First and foremost, they are doing is scheme for training of masons, carpenters, and barmenders. Well, actually, that is really important. I was just going through the list of topics which you would cover in the coming days. One is theory to practice. If I could see, it is, I think, on the last day of our conference, it is non-engineered construction, theory to practice. whatever we discuss, it has to be brought into practice actually. So we'll dwell here, some things will come into design, something will actually go into the construction part. So this important topic they are covering, this training of masons, actually in the rural areas, in urban areas where we have we have TCP regulations, somebody is there to check our maps, some regulations are there. But in the ruralized areas, which in case of Himachal, maximum part is the rural area. In fact, our first point of contact is the mason. We speak to mason, ask him कि भाई कितना खर्चा लगेगा, कितने समय में बना लोगे. He is our first point of contact. So for him, it is if he is having some knowledge of these kind of structures, he'll definitely it will go a long way in building these kind of resilient structures. So in the Himachal, we are doing this important activity. In fact, before this pandemic Corona started, we covered 11 districts of Himachal. In fact, I was earlier posted as additional deputy commissioner, so also I also had the opportunity to get associated with this program. We were able to train 100 odd masons, and we had the program for 5 days. It was meticulously planned program, because if you see these people, they are hand to mouth. They work in a day and then they will eat in the evening on that, and then eat in the evening. So we have to support them for the training programs also. So what government did, they included some honorarium which was equivalent to their day's earning for the n number of days where they will take the training. So this is one important scheme which is going on presently in the Himachal. And another is we are also covered under this National Seismic Risk Mitigation Project, which is World Bank aided project. And I would like to inform all of you that Technical Education Department is an important component of this project. We are planning with the state to have a technical demonstration unit TDU in Sundanagar subdivision. There's a place called Kongu. We had government land there. It will be eventually associated with our Jawaharlal Nehru Government Engineering College, Sundanagar, where we have this faculty of civil engineering, and they will eventually manage it. This TDO will be a big project which will have demonstration units, then training halls, and then training facilities for all, for researchers, for students, for masons, and all categories. It will be a one focal center for the entire Himachal with our focus on this resilient structures and design. One part of this project is the technical demonstration unit. Another important part is we will be retrofitting n number of buildings in Himachal. In fact, 376 important lifeline buildings have already been identified, which includes hospitals, schools, important government offices, some airstrips also. And in the first phase, 198 buildings have been prioritized. So funding has already been approved by World Bank, which will eventually come to the state, and already work is being done in this field. So these were the few highlights which I wanted to throw light upon, and I hope this 5-day workshop will in fact bring a big change and drive all of us towards making resilient and safe Himachal and our entire country. Whatever you dwell in this 5 days conference, and I request all the participants to percolate it down wherever we are in our institutes, wherever we are in our universities, and in future also I request Dr. Sharma that such kind of associations, such kind of conferences, they should be organized more and more. I request, I am really thankful to you that actually you involved me in this conference. We have a lot to work upon. In fact, under Technical Education Department, maximum faculty members, they've been trained by CBI Roorkee for this Masons training program. So we are already having association with many of the institutes. Another structure safety audit of lifeline building, which is being undertaken by the participant institute. In fact, one of them is IIT Mandi, CBRI Roorkee, and NITR Chandigarh. They have been given few districts to carry about this profile study of this lifeline building. So all these activities are being undertaken to make our state safe with this perspective. So I once again thank you so much, Dr. Sharma, and I request you to keep on blessing me in the future as well with these kinds of opportunities. And my best wishes to the entire faculty and UIIT and all faculty members and participants. Thanks a lot, sir. Thank you so much.
Thank you so much, sir. Thank you for enlightening all of us with your words of wisdoms. Once again, on behalf of University Institute of Technology, Himachal Pradesh University, I would like to thank you for giving your precious time for this occasion. And also, sir, it will be great pleasure for us to hear from you again in our future events also.
Thank you. My pleasure. Thank you.
Dear participants, we are sharing all information of day-to-day schedule on WhatsApp group, and the link of WhatsApp group has been already shared to all registered participants by mail. Also, for any query, you may contact coordinator of this program, Dr. Mahesh Sharma. So finally, on behalf of UIT HPU, I would like to take this opportunity to place on record our hearty thanks to chief guest of today's program. Also, I would like to thank all participants for being part of this program. Thank you so much. Now I request all of you to kindly leave the session. Once again, thank you so much and have a nice day. Thank you.
Yes, Dr. Anjali, so we don't have much time. So rather than leaving, we'll start our next session at 11 o'clock. The lecture by Dr. Shantanu Sarkar. So I think we'll be starting it right now.
Okay, sir.
Yeah, initially we thought that there will be 3-4 minutes gap, but I think we already have crossed that limit. So we will be starting the lecture. Thank you, Dr. Anjali, for your time. Dear participants, I take this opportunity to introduce our first speaker of this program and first speaker of the day, Dr. Shantanu Sarkar. I hope Dr. Shantanu Sarkar can hear me. Yeah, very warm good morning to you, sir. It's my privilege and definitely a proud moment also to introduce my guide also, and with whom I have worked for a long time, Dr. Shantanu Sarkar. So Dr. Shantanu Sarkar is presently working as Chief Scientist and Head of Geotechnical Engineering Division, CSIR Central Building Research Institute, Roorkee. He has done his PhD from IIT Roorkee and postdoc from EPFL, Switzerland. His specialization is in the area of engineering geology, and with sub-area of specialization includes landslide disaster mitigation, geotechnical investigation, and slope stability analysis using remote sensing and GIS application in geohazards. He is the recipient of many prestigious awards at national and international level, which includes National Geoscience Award in the area of disaster management by Ministry of Mines, Government of India. He is also the recipient of a prestigious fellowship, Boycost Fellowship, given by Department of Science and Technology, Government of India. His experience is very much more than my age, that is 32 years. So it's a wonderful and proud moment to that he has given time from his busy schedule to be the speaker, not the speaker, the first speaker of my program on disaster resilient infrastructure. Sir, I thank you once again. When you were contacted, you never were much hesitant about timing, or I still remember that you have planned to go to Jammu and Kashmir, but then you still said that I will try to get connected from that part also. So I welcome you, sir, to this program. Thank you very much for giving this opportunity that I can listen to you also from this department through online mode. Thank you, sir. Over to Dr. Shantanu Sarkar.
Thank you. Thank you, Dr. Mahesh, for nice introductions. So it is my pleasure that I'll be giving a lecture to your department, and you are now the coordinating faculty of civil department. So it is also a good opportunity for me to speak to give a presentation in your department. Let me share the slide. So okay. Is it visible?
Yes, sir. It's perfectly visible.
Okay.
Yes.
And audible also?
Yes.
So shall I start, Mahesh?
Yes, sir. You please start, sir.
Okay, fine. Thank you. Yeah. So, good morning to all the participants, faculty members, and students. For next one hour, we'll be talking about different landslide hazard assessment techniques and mitigation strategies, and my own experiences in landslide investigation in Himalayas. Yeah. So my outline of presentations is like that. I'll be talking about some landslide problems in Himalayas, geo-investigation and stability analysis, and then how we do the hazard assessment, and then a few examples of mitigation measures. Now, for any infrastructure development, landslide hazard assessment, as our chief guest also told that we should be knowing that where the landslide is going to happen. So that part can be taken care of by carrying out landslide hazard assessment study. So for any infrastructure construction, infrastructure development project, landslide hazard assessment is a very essential task. Now, sorry. If you see the landslide scenario, this is some data. Now, from this, this is only the fatal landslide data of say 10 years. And you can see here that United States and India has got a very large number of fatal landslides and number of events. If you see this Uttarakhand, you can see my cursor, right?
We can see it, yes, sir.
Okay, so in this, if you see the Uttarakhand recorded landslides, say from 2010 to 2016 or 17 data, you can see that we have approximately same number of landslide, except in 2013. This is due to, as you know, that Kedarnath disaster, June 2013. So probably number of landslides are pretty more. If you see the rainfall data of Uttarakhand, then you can see that mostly the rainfall is pretty high during the monsoon season. This is the area where you have from rainfall from May to August. And also you can see the maximum observed landslide, this red one. This is significantly higher than other years, and this is 2013. Again, this is due to that Kedarnath disaster, recorded landslide and debris flow. Now, fatal landslide in Himalayan region, if you see the distribution of fatal landslides of Indian region, particularly Himalayan and Western Ghats and Northeast regions. So we have seen, that landslides are triggered mainly due to rainfall, but these days I can see that the landslides are being triggered, many landslides are triggered by construction activities. And the record says that 30% of in India, landslides are triggered by construction activities, mainly road construction, building construction. As you know, widening of road is happening. So there are many landslides. You can see this in this year also. There are many landslides which occurred along the roads, and those roads are being disturbed, and not probably mitigation proper measures were taken. So the landslides are happening. Now, in Himalayas are prone to landslide because there are different rock types, tectonic zones, various topographic relief slopes of diverse nature, and structurally deformed rocks have been subjected to severe erosion by toe-cutting action of rivers. And then recent years, as you all know, because you are in the hill state, so the hydroelectric project, large scale construction activities, mining, quarrying, so many things are happening. So these also, destabilize the vulnerable slope and cause landslide occurring. So you take any example type of landslides, you will get, in Himalayas, like whether it's a rock slide or it is a rock fall, the debris flow, debris slide, subsidence, everything. So all type of landslides we generally get in our Indian Himalayas. So this is, you can see that our geology is very complex. We have different rock types, we have thrusts, tectonic faults, we have so many epicenters, and also the unplanned road constructions. Now, when we see the causative factors, so one is your internal factors and external factors. When we talk about internal factors, it is mainly geological structural setup. What type of rocks is there? Whether it's a metamorphic rock, is it igneous rock, is it a volcanic rock, and what is the weathering condition of rocks, and those rocks associated with faults, shear zones, discontinuities, and then comes the strength characteristics of rock. So this part is for the geologists, and this part is for the geotechnical engineers. So in between this is the engineering geologist, which we generally try to give knowledge of geology to the geotechnical engineer, and the knowledge of little bit geotechnical engineer to the geologist, so that we can plan a better landslide disaster mitigation program. So this is what about the internal factors, and then the external factors are mainly a rainfall, earthquake, and anthropogenic activities that you all know. Now, landslide disaster in Himalayas, if you quickly will show you some photographs or some pictures to have a knowledge or have a brief these things about landslides. So this is one is the Malpa landslide, which is 1998, and there was about 200 deaths. Then we have a Fata landslide. This landslide is along Utkashi Kedarnath road. So there is a debris flow, and some schools were affected. You can see the national highway and the damaged schools. Around 10 persons were killed there in this landslide. Then this is the Uttarkashi landslide. This is, you can see the pre-landslide scenario. So this mountain is called Varunavat Parvat, and this is the Bhagirathi River, and this is Uttarkashi township. The landslide occurred. You can see the post-landslide scenario, how the debris slide occurred, and it has been channelized. Three channels were formed, and there was a huge damage of the buildings and roads. But fortunately, there was no casualty, because when it started, people were very much informed, and we also went and do the hazard and risk mapping. So there was no casualties, but there are heavy damage to building and roads. Now, if you go to Uttarkashi, you can see that there was a lot of mitigation measures taken up by GSI and THDC has implemented. So this is a very good example. If you go to Uttarkashi to see what are the measures they have implemented. This is one debris flow on Munsiari Road, Pithoragarh. This is 8 August. So this debris flow, there are many villages which are situated at the bank of the river, and probably 3 villages washed away, and I think around 40 people were killed with this debris flow. It happened suddenly along this drain. Then this is a mud flow. This happened in front of us. So suddenly there was a rainfall, and then there was a mud flow, and which covered highway, and you can see these temples and buildings were also covered by mud flow. This is a typical example of slope failure. This is Bhatwari in the Uttarkashi Gangotri highway. You can see that first this cracks appeared on the road, okay, and then slowly this crack has initiated, and you can see that this is actually the slip circle. So from this part, the subsidence has occurred, and the whole market and buildings they slided down to the river. And I can show you that this building, this house, which is situated here at the road, it came down to this at the bank of this river, and it took around 4 days. It slided down. So it was a very slow slide, and very typical, very good examples of a rotational failure. There was no casualties, but the whole village was destroyed. Then the Kedarnath tragedy 2013. This is what is before the disaster, and this Kedarnath town before the disaster. This is the Kedarnath temple, and this debris and all rock and water, the flash flood was there, and after the disaster, the situation was this. So we many people of around more than 5,000 people lost their life, and there is a huge damage due to this Kedarnath disaster. Now, recently, as you know, that Tapovan Ganga disaster, 7th February, everyone knows it, and this it occurred from a, basically it is a, initially people thought that it is probably Glof, there is glacial lake outburst, or there is avalanche and all, but basically this is a rock slide. So a rock slide along with a lot of snow and ice, it fell down this river, and Roniti River, and then, this is a crash zone, and this is Roniti Glacier. So it goes like this, and then here, this is a very good example of a creation of landslide dams. There was a partial landslide dam. Fortunately, it didn't burst because there was some channel. So slowly this water came downstream, so there was no immediate risk of flash flood, but there was a landslide dam. So huge debris has blocked. So this type of landslide dam, they are very important, because we should know that what are the potential areas where the landslide dam can be formed. Because once the landslide dam is formed, there will be creation of a large reservoir. And due to immense pressure, when this temporary dam burst, then there is the heavy flash flood. 1972, there was a heavy flash flood in Alaknanda River, that is known as Alaknanda tragedy. So those type of landslide potential dam also need to be monitored and to be assessed. Anyway, so this debris and this debris flow came down here, and this is the site, the Tapovan Vishnugar hydropower. So everyone has seen this in the TV, that there's how the people were running on the top of the hydropower project, and all they lost their life. So this is a close-up of this rock block which fell down, and so you can see here again. See here, this is what the rock block. If you see carefully, this is already there was a crack here. So it is slowly, crack was opening here, and suddenly it fell down. You can see the hollow portion. So from there, it fell down as a huge rock block which fell down the river, and then started along with this ice and debris and everything. So it created a disaster. You can see here that this is a type of wedge failure. So this came down, and you can see here the debris flow mark, how above this river bed it was there, and it blocked this tunnel where so many laborers lost their life, and this is what the hydropower project was damaged, and laborers and other workers were lost their life. Okay, so now I'll show you some photographs of landslide problems along Himalayan roads. So this is a landslide occurrence along the highways in Indian Himalayas, where high rainfall intensity and other infrastructure construction. So you can see that this is a national highway going to Badrinath, and after the landslide has occurred, it is so risky. And you can see here how this cars, vehicles were so small. In fact, Dr. Mahesh was with me when we went to the site and collected data and did some stability analysis and published a paper in Current Science. So Mahesh knows about how big is the rock chunks which slided down. And these are some example of the debris slide. You can see here there's a type of planar failure that along the discontinuity. There is a potential site just 18 kilometers from before Badrinath. This is a potential site for debris flow. So those type of, we are on the road, but we don't know what is happening behind this hill. So those parts has to be assessed, has to be identified using satellite data, so that we know that yes, there is a hazard, and people should be warned while crossing this road. So those type of hazard assessment is very essential. This is what the debris slide, you can see that this border road people are clearing, and it also happened in front of us. Because of the road construction, the huge debris came down. Okay, so now giving a brief idea, give knowledge about what happened in the landslide, different types of landslide. Now coming to landslide hazard assessment. Now when we talk about landslide hazard assessment, we should see or consider that what scale we want. Now suppose we want to have a hazard map of the district, or maybe 100 square kilometer or 200 square kilometer. So in this situation, what we do is that we prepare several factor maps, so the factors which govern the stability of a region, say like slope angle, rock type, fault lineament, drainage, soil map, land use land cover map, and drainage map, etc. So we have a data input from topographic map, field data, your published map and all. Okay. And then we process the data, the knowledge-driven approach, statistical approach. So actually, basically, what we do that we try to correlate the factors along with the existing landslide, so that we try to see that the areas which are prone to landslide, So from the existing landslide, we go to the potential areas where landslide can happen, and we prepare a landslide hazard map. So if the landslide hazard map looks like this, these are all, this is satellite data, this is a digital elevation model, this is a slope map. So all these maps have been prepared in GIS. So this is drainage map, lineament, land use land map. So all these maps we study, we prepare, and then all these maps are integrated in a GIS platform, and finally giving some weightage to the different factors, we prepare a hazard zonation map. Now, this hazard zonation map says that, say, for example, it has been classified into 5. This red part are the areas which are maximum very high hazard prone area, and the green is a least hazard prone area, the stable slope. So whenever we try to do some district level plan or project, such type of hazard map is required. But again, it depends on which scale you want. If we are having constructing some buildings, some bridges, then site specific study is needed. This type of study won't help you. But initially, for a large scale planning, this type of hazard map will be useful. Now, see, sometimes we also should know that along the road, which are the hazard prone, landslide prone areas. So for that, you can see here that this is a high resolution satellite data, and this is from Pipalkoti. This is along Chanda River, right? Pipalkoti, this is Joshimath, and then the Badrinath. So there are some zones I have created where we know that there are some landslides. So for those landslide, what we have done is that we roughly estimated the landslide volume, because landslide intensity is a function of volume and velocity. If we know the time of occurrence of landslide, how many times the landslide has occurred, then it is very good. Then we can add this thing in landslide intensity. But unfortunately, we don't have such records that at particular site how many times the landslide has occurred. So with volume of landslide and the speed of landslide, we can prepare a landslide hazard map. This I'll show you here. That this is the Alaknanda River, and these are on the satellite data we have mapped this landslide. So with a high scale, high resolution remote sensing data, you can very well identify this landslide. And of course, then you go to the site and check the validity of this maps. So once you prepare this map, you can see here that this map, this is the photograph in the field, and this is the map. Similarly, this is the landslide we have mapped, and this is your photographs. Okay, so like that, all landslides were mapped, and from this we can calculate the area, and in the field we can estimate that how much volume is there, which will be going to slide. So based on this volume and the type of landslide, like if it is a rock fall or the debris flow, the speed is high, and if it is a subsidence and the rotation failure, then speed is low. So based on the type of landslide and the volume, we can prepare a hazard map. That's what we have prepared along the road. You can see that, Pathal Ganga, Helang, so different zone, hazard zones were marked, but you should note here that I have only considered the existing landslide. I have not considered the potential landslide areas, only the existing landslide, so that we can have a priority that which landslide is more important for plannings of mitigating measures and all. Okay. So such type of hazard assessment based on landslide intensity, based on landslide inventory, can be prepared. Now you can see here that, based on that study, we have, this is the Vishnu Prayag hydroelectric power project here. This is the Vishnu Prayag. This is the Vishnu Prayag river, and this is the Alaknanda river. So this is a junction, and this area is known as Hathi Pahad. Okay, so this Hathi Pahad is very dangerous. It is very prone to landslide, as we have studied. Now, when we studied in 2013-14, so we found that you can see here the road, and the slope is very prone to landslide. There are a lot of rock blocks situated here. And also here you can see that there is a chances of planar failure here. So we mapped this area and we say that this is a high hazard area. So you can see here that 2015, the landslide is occurred. Then 2017 again, when we went, landslide occurred. And now, a few days before, 28th June also, this year also, in the same area, again landslide occurred. So such type of hazard area should be marked depending on the field investigation or depending on the geological rock type, geological discontinuity, as I told earlier. Now, coming to a different scenario of landslide hazard assessment based on slope stability analysis. That's what the geotechnical engineer and civil engineer does. That, the previous one was little bit qualitative, but now it is a quantitative hazard assessment. So for that, what we do is that we do the field survey, geological, geotechnical data collection, slope stability assessment. Then you can see that recently for the rock slopes, we have carried out certain studies for slope stability assessment, that is based on kinematic analysis, GSI, that is geological strength index, rock mass rating, slope mass rating. This is absolutely for the rock slope. For the rock slope and soil slope, again, we can have a numerical modeling techniques. That is a classical limit equilibrium methods, or it is the finite element modeling. And then there are different techniques these days. You can use some software also where you can find out that which criteria you want to work on. It is a Moore Coulomb criteria, failure criteria, or a Hook-and-Brown failure criteria. And then, of course, from the rock mass classification techniques and from numerical modeling technique, both you can integrate and find out the stability grade, and then you can prepare a quantified landslide hazard assessment as a hazard map that is based on a factor of safety, right? So it gives a quantified landslide hazard map. I'll show you some examples that some data from the Rudprayag-Sonprayag road. So now you can see here that this is a discontinuity plane, and this is a discontinuity plane, and this the intersection of this two discontinuities, there is a chance of wedge failure. Similarly, this discontinuity plane is shows a planar failure. So generally, geologists, what they do, that they plot those discontinuities, like in J2, J1, two discontinuities, and then the wedge failure and the intersection of the two joint planes, which is parallel to the slope. So like that kinematic analysis, we decide that what type of failure is going to happen, whether it is a wedge failure, is a planar failure, is a toppling failure, or if it is very jointed rock and soil, then there could be a chance of circular failure. Now, geological strength index these days is a very important parameter, because and it's very easy that you can evaluate this GSI, because it depends on the rock mass structure, whether rock mass is massive, or it is a blocky, or is a very blocky, the disturbed, or disintegrated. So based on the type of rock mass structure and their surface conditions of the joint, there is a chart by which you can estimate, you can calculate geological strength index that varies from 0 to 100. So if it is 100 is the very good rock mass, and the 0 is 0 to 10 is a very bad rock mass. So now, but then you should see here that now we are not talking about the strength of the intact rock. What we are studying is the strength of the characteristics of the total rock mass. And now this is very important, because what we do is that when we do the calculate or compute the strength, determine the strength of the intact rock, we take rock samples and come to the laboratory and did the right shear triaxial test and get the compressive QCS, that is compressive strength. But actually important is that rock mass, because when you take the intact rock, naturally the strength of the rock will be very high. But when you consider the rock mass, that it includes the joints, fracture, and the material inside the joint filling, that is joint filling material, then naturally the strength of the rock mass is to be low, and this gives the actual condition. So sometimes the geological strength index is very important, and these days people are doing that they are getting a lot of the relationship between the GSI and the different strength characteristics of rock. So if you know the GSI, there will be you can calculate many parameters from the GSI. There are many relations. I am not going into detail of that. So and then we have a rock mass rating. So if this rock mass rating is based on uniaxial compressive strength of rock, UCS, already RQD, spacing of discontinuity, that is a joint, condition of discontinuity, and the hydrological conditions. So once we know the RMR, from RMR you can calculate slope mass rating. So you add with this RMR different factors. So these factors are basically depend on your relationship between the discontinuity plane and the slope. The discontinuity plane and the slope is parallel, and otherwise, if the discontinuity plane is dipping inside the hill slope, so the scenarios are different. So based on the relationship between the slope and the discontinuity plane, there are factors F1, F2, F3. So along with that, RMR basic plus this F4 is your adjustment rating for excavation. So you calculate the SMR. Now SMR 5 classes of stability varies from 0 to 100. These are some of the things is there in the literature also, and if you want, I can send you some publications, so that if you want to work on that, you can always get it. Is very easy. Now the field investigation generally for rock mass classification and such type of stability analysis, what we do is that we see the rock type. We have the rock mass structure, the different joint attributes, that is joint spacing, then joint deep direction, then the condition of joint, that is the roughness, weathering, infilling material, waviness, joint alteration, and then volumetric joint RQD, and then joint shear strength properties, that is joint roughness coefficient, and joint wall compressive strength. There are now, this Smith hammer, which is civil engineers that use for determination of concrete. So we also use different Smith hammer for getting the universal compressive strength of rock joint, right? So from this hammer, you can have the UCS. Of course, there is a point load testing machine also. So if you bring the lumps of some rock samples, that also can be tested in the point load machine, and you can get UCS. And then hydrological condition, and as I told that the relationship between the slope and the geological discontinuity. So all this data, if we collect, we can very easily calculate GSI, rock mass rating, slope mass rating, and also in the kinematic analysis, and we can have a estimate of stability grade. So this is how we we take some slope profile. Here you can see that is the Smith hammer to have a joint compressive strength of this, and this is a point load machine. So we bring rock samples and then estimate the UCS. Okay, and these are this is the spacing of joint, this is spacing of joint, this is opening. So all this parameter we calculate, we determine in the field. So I can tell you that here, see, this is a stable. So this is a massive rock. You can say here, this is a partially stable. So this is a very blocky, and then this is unstable, very blocky with some shear zone, and this is completely unstable as we have thrust zone. So this type of different rock types, different rock slope we study, and then define the quantitatively the different stability grade. So based on this, I can show you this is the map from Rudraprayag to Agastmuni, that is along the Mandakini river, and you can see this is the land use map, and this yellow, green, red, these points are the slopes where we have calculated the slope mass rating, and based on this we classify different slopes. You can see that wherever we have found there's a problem of slope stability, we have calculated the slope mass rating and classified into 5 classes. And this is a DST project, and DST has published an atlas on that. So that is available with the DST. Along this project is from Rishikesh to Kedarnath, the whole along the Alaknanda and the Mandakini river. Now, some example of stability assessment of Uttarkashi Bhattuwari Road. Dr. Mahesh or Dr. Anjali, please tell me when the time, because I'm not looking at the...
Sure. You please carry on.
Time is there. Okay. So now, debris slide and subsidence. So this is the typical example of a sinking zone. You can see here this is the present road. Previously the road was there. So slowly the road has gone down. So it is a very typical example of circular failure. Slowly it is getting subsided due to this is very close to main central thrust MCT, and this is all debris, gneissic rock debris material, and slowly the road is getting subsided. So this is a sinking zone, you can say. Then you look at here. This is when you drive through this, you don't get that. Okay, this is something. There is no landslide. Apparently, there is no landslide, right? But the important part is that you can see the different joint plane. This is J1 is one plane, J2 is other plane, J3. So this joint, there is some wedge is making, there's a planar failure, and you can see this rock block, it is here. So this block actually fall down just before us only. This type of rock fall are very dangerous. So even if this is not actually look like a landslide, but this type of small rock blocks where there are open joint, where there is a chances of wedge failure, planar failure, this should be marked, this should be mapped, so that any incident, fatal incident should not happen. And you really, these days you heard that certain rock blocks came down, and that some vehicle were trapped and people were killed. So this type of zones are also needed to be studied and to be marked basically along the road. These are some of the, then, what I told here. So what we did is that this type of, slopes we identified, we mapped, and with all this data, we calculated the factor of safety. So in the dry condition, factor of safety is 0.97. I mean, almost marginally stable, you can say, and then the factor of safety with the wet condition, it went down to 0.95 and then 0.91 with the pseudostatic loading. So these are the photographs of the site, and we several this type of slopes. We calculated the factor of safety, and then we prepared a hazard map based on the factor of safety value. So if you see the map, okay, and also, sorry, I want to say one more thing, that there are many, as we talk about the infrastructure, there are many bridges, and some apartments, some bridges, there is a problem of landslide. So those areas where you find that there is a problem of landslide, that should be also studied, and a stability assessment has to be carried out. So like that, we also did some exercise, and this is the Devprayag, and we found that there is a problem of landslide here. So we calculated the data and then did some analysis, stability analysis. We can see here, this is the bridge, and it is a Devprayag, and there's a chances of debris slide here. So we calculated the stability factor of safety, which is coming at 1.1, so is the marginal. And with wet conditions, when we give the pore pressures into this model, we get a factor of safety 0.65. So all these areas where you have a vulnerable slope along with some infrastructure, here it is, bridges we studied. So that type of study also can be carried out and should be carried out. So as I told that, this along the road, we did several such type of small rock slope, soil slope, debris slope. We did some exercise, did some study or stability analysis, and based on this factor of safety, we prepare a hazard map. So you can see here that we have marked this, where the factor of safety is less than 1, we have marked it as a high hazard area, and factor of safety 1 to 1.2, we have kept a high hazard, less than 1, very high, factor of safety 1.2 to 1.5, moderate, and more than 1.5, of course, that is the stable slope, so there is no point of studying those. So this is also another way to prepare hazard maps. So now you see, when I started, I told that depending on the scale, if you want to prepare a hazard map, so you will go for a large, small scale landslide hazard map. So maybe the area will be 100 square kilometers or so. Now come from there, you have a hazard assessment qualitative, and then suppose you want to have a very specific landslide hazard assessment along a, say, 50 or 60 kilometer along the road, or the site where you want to construct some infrastructure, then such type of quantified hazard assessment can be done and should be done. Okay. So this is all about our landslide hazard assessment. Now I'll show you some examples of mitigation measures, right? So, these days, the type of mitigation measures are plenty, and you just Google it, you will get all sorts of mitigation measures, but depending on the type of mitigations, type of landslide, you have to decide that what type of mitigation measure you should adapt and you should prescribe. Now, this is an example when we are, I think, 2 years back, when there was a road widening and people were constructing road here, I think along the Alaknanda River, and you can see that just after 3 months of constructing this road and these things, they constructed a gabion wall to support the slope, and after 3 months, you can see the condition. What does it mean? It means that they have constructed the gabion wall without investigation, without any data. Just to construct a gabion wall, they have constructed, but they have not really studied the strength of the material and designed and calculated the stresses. So there was a rain, and then it just collapsed. So what I mean to say is that for different properties of rock or different properties of soil, one should model the slope, and based on this, one should prepare the remedial measure. It is not like that we have to construct a drainage. So we construct a drainage without investigation in the area. So whenever we prescribe a mitigation measure, then we must at least study the geotechnical properties and the geology of the area before we really design a mitigation measure and implement it. So this is then a landslide. This is called a Netala landslide. Is a chronic landslide in Uttarkashi region. Okay, and you can see here that there were 79 events of landslide occurrence from 5 years. And the maximum debris volume of about 1,600 meter cube was there slided down from this slide. So we did. Yeah, so we did some, drilling on the slope so that we can prepare some litholog that what type of material is there. So we did drilling up to 45 meter, and the material of the road above the road is highly weathered and schist, and below the road, if you see, below the road is a rock totally, quartzite rock, very strong rock. But above this road, there is a very pulverized, there is some, I cannot show it, but there is a shear zone here, is a very prominent shear zone. So because of shearing of these rocks, they are pulverized, and there is a overburden of few meters, which frequently comes down and block this road. So these are you can see the type of debris material collected from the drilling. And then we did the factor of safety calculation, stability analysis, the dry condition, wet condition. And you can see here, in wet condition, this is the red part, which maximum displacement and maximum shear strength is there. So we always calculate the factor of safety in dry condition and then the wet condition and see that how unstable it is before you really going to have a remedial measures, because you have to determine the factor of safety before you implement, before you include the measures, and then to increase the factor of safety, you prescribe, you model some mitigation measures, and then you again calculate the stability. You can see that how much factor of safety has increased, right? So here in the same slope, what we did is that some geosynthetic anchored geosynthetic we have prescribed, and we found that factor of safety unreinforced when we have not applied any reinforcing material. This factor of safety got 1.04. When applying this geosynthetic anchors, we found that the factor of safety is 1.5, and depending on the anchor length, when the anchor length is 10 meter, definitely the factor of safety will be more. When the anchor length is less than that, 5 meter, then this factor of safety will be less. But as you know, as in the inauguration, the chief guest was telling that we have to see the cost also, right? So it is not like that without calculating, without thinking of the cost, we will say, okay, 1.7 meter, ठीक है, 10 meter, sorry, 1.7 factor of safety you are getting with the 10 meter. तो ठीक है, चलो भाई, हम 10 meter का ही anchor इसका implement design करते, but it is not true. Okay, it is not feasible. So we have to compromise between the cost and the safety factor. Similarly, here it is something we have same landslide. We designed some micropile, and see that how much we increase the stability factor of safety. So factor of safety of unreinforced slope we found 1.04, and the estimated factor of safety with some reinforcement maximum we found 1.72. So what we should do that while studying a landslide, we first see that, okay, what are the probable measures can be designed, can be considered here, depending on the depending on the cost, depending on the, of course, the availability of local material and all those things. Okay, so we have 3-4 measures, and then out of 3-4 measures we see that which combination of measures give you a better result. Okay, as I told just now that this is a landslide, and Dr. Mahesh was with me when we are studying this landslide. So this is the area where you can apply some soil nailing. This is a Gabian structure. You have a drainage, and they again a soil nailing. So this type of landslide slope, you can say that okay, these are the places, it's the type of measures you should implement. Then you design the measures along with the slope. So we have a gravity wall here, and we have a concrete gravity wall here, and somewhere here we have a soil nailing. Now, instead of concrete gravity wall, we have a Gabion wall, okay? And then calculate the factor of safety. So it is coming, say, 1.35, here 1.31. And then the scheme was then again we changed the scheme, and we found what we did is that now soil nail plus Gabion wall plus micropile. So again, we calculated the factor of safety is coming 1.4. So depending on the fund or the money we have, and see the importance of the slope, we can design integrated the different type of measures, and finally we can say whoever is the construction agency or the government of Uttarakhand, or maybe in case of government of Himachal or PWD, that this is the scenario, this is this thing. Now you decide that which package of measures you want to implement. So we can decide, and it can be implemented. Okay, some typical drainage measure I am showing you. This is a surface drainage, and this is example of subsurface drainage. Here you can see this. This is an example of from Sri Lanka. So, sorry. So this, based on only the subsurface drainage, the whole slope was stabilized without doing anything else. They have only control the pore pressure and stabilize the slope. I'll show you this. So this is the landslide, and the railway track was damaged. And what they have done is that along the whole slope, they have provided this subsurface drainages for the whole slope. And these are the piezometers from where intermittently they check the pore pressure, rise of water table, water level. So based on the drainage measures only, without doing anything, surface drainage and subsurface drainage, only the two things they have, they were able to stabilize this slope. Now there are retaining structure. There are different type of retaining structure. I think you also know all these things. The masonry retaining wall is there, creep wall is there, Gabion wall is there. So it gives a support to the slope. And this is I want to show you. This is what I told that in Uttarkashi landslide. This is a rock reinforcement. So when the rock blocks, jointed blocks are large, then you apply rock anchors. Okay, and when there is a very the discontinuous planes are fine, the thickness of joint planes are not more. It's a weathered rock or foliated rock. Then you can apply rock bolt. Okay, so it's a rock anchor and the rock bolt, and then this you can see here that these are the subsurface drainage. Okay, and this is a surface drainage. So in this Uttarkashi landslide, in fact, they have implemented many measures. So this is they have the slope. All the whole slope was shortcutted, and with this shortcut, you can have a rock anchor, rock bolt, subsurface drainage, surface drainage, and at the top they have with this geogrid maze. There's a vegetation. This is our all vetiver grass. So vetiver grass also, because once they have laid down the geogrid mat, so the erosion was less, and you can grow the vetiver grass. So it is a type of bioengineering measures you can make on. So that's why I was telling that if you sometimes go in the Uttarkashi, you must go. There is a road by which you can go there and see the landslide measures which were implemented by DHDC. Okay. As I was telling you, the rockfall measures, these are very important. These rockfall measures are, different type of rockfall measures are there. Like these are rock catch fences. There is the There are different types of rock, there are different types of slope blocks. So depending on the size of the block and the steepness and the type of rock, you can prescribe some rock catch. This is called rock catch fences. In India, we don't see much of this use, but in the European country, particularly in Norway and all, because those areas are very prone to rock slide. So they are very much, all the hill slope, they use this rock catch fences. For rockfall, this thing, we can also prepare some ditches. The rockfall will happen, occur, and then it will accumulate in the ditches. The problem with such type of ditches is that we don't have much space, in the road. So it is very difficult that we prepare some ditches. Okay, so whatever we have to protect, protection measures we have to do on the slope itself. So they are a rock trap well, and this is very easy. There is a rock slope where slide, and you have potential debris or rock. So you put some gabion wall, in a zigzag way. So even if there was a rock fall, the impact energy will be less, and people will be saved in the road. Okay, so such type of gabion wall. So it is some type of kind of a rock barrier. So there are some barrier you construct on the steep slope so that the rock fall will not happen directly. So we can, the road and the vehicular traffic are safe. Yes, this is now in India. People have started thinking on this, and this is very good. This is called rock fall shelter. Okay, so what is happening here? That rock will fall down on the shelter, on this, there's and after that, from here it will jump into the valley. So the people were safe here, right? So depending on the type of rock, you have to design this shelter. If this shelter, that rooftop is constructed, this is a concrete. Okay, it may be steel structure, but if we can prepare a material which has a very good elastic property, so that the rock will come and bounce and then fall down into the valley, then it will be good. So such type of structure can be designed, and it is very good. Now you can see here that if you go to Sikkim, so before reaching Gangtok, there is a place called Rangpo. So there also they have, it is not perfect a typical rock set, but it's a half tunnel sort of thing, So that the vehicular traffic should not be trapped by any rock boulders. They have constructed a half tunnel sort of thing. In CBRI long back, they have constructed some drum retaining wall. This is very cheap and easily constructed. So what has been done is the empty bitumen drum wall, which is there is no cost because you get freely when there was the road was made by tar. So this is vertically anchored and horizontally anchored, and this hiding debris were filled up. Okay, so this type of drum wall is very cheap and very good. In fact, there is a, there is a famous landslide, Kaliyasu landslide, and it was constructed in 88 or something like that when I came to CBRI, and I monitored this thing, and this drum wall was stood for is 100-meter long, and it stood for around 18 years, and unfortunately because of road widenings, the people have removed this drum retaining wall, but it was actually very good mitigation measures. Then we have also constructed some gabion wall in the Mussoorie, and this is a typical example of pile. So this is a wooden pile. So you do some terracing with this pile, different benches, so that you are decreasing the steepness of the slope. So this type of instead of some sort of, you can say, micro pile or wooden pile, now we are using concrete pile. So wooden pile can be also used. Now after this measures and all, what I need to want to tell you here that when we construct a major infrastructure, okay, so while constructing the major infrastructure, we should have a very good economic survey, and we should know that when we are constructing something, what is going to happen, when you construct a infrastructure. So here is the case of a airport, which is in the Sikkim and Greenfield Airport. Now the airport has been constructed. You can see here. So what happened is that this was a hill. Was a hill, and it is a cut and fill structure. So this is a fill material. To support this fill material, a reinforcement soil wall was constructed. Okay, and it is around 120 meter. I think 1.5 kilometer long RS wall. At certain places, the wall was 20 meter or 30 meter high. But here, the height of the wall is around 75-80 meter. Because of this, construction of this wall, there was a tremendous thrust generated here, and all the houses here were damaged. Okay, and also because there was some villages here, so when you did the cutting here, so there was a distress, and all the houses here also slowly get damaged. Okay, what I mean to say is that before you plan that this type of airport or something like that, you should know that if you are doing that, what is going to happen. So it's better that you evacuate those houses initially like that, because here what happened, they didn't thought of that this type of damages will occur. So there was some problem of the villages and all these things. So I'll show you this. See, this is what I was telling, around 80 meter high reinforced wall. There is absolutely no problem. I mean, I think in India this is the first time this is so high retaining structure that was, I think, made by Motmac in Bombay with the material from Macquarie. So you can see here that how they have prepared, and where the height was is around 20 or 30 meter. It was good, and they have there is a geogrid mat, and then there is a good vegetation here. But there was, and you can see here that due to construction of this wall, this building were damaged. Initially, it was standing. Now, this is the photograph of 2 years back. So now this building is also not there. It is also damaged. And the situation is that. So what I was doing here is that this part, because of some damage and all, I am now monitoring this wall, this part. Okay, and I am getting some movement. At the in the wall which is 20 meter, there is no movement, but wall was 80 meter. Surrounding places, I am getting sometimes 50 centimeters, sometimes even 1 meter, subsidence because of this heavy wall. And the other thing which I want to say here, that when you constructed such retaining structure, the structure should be instrumented. Because the problem is that they didn't have any instrumentation on that. So if you you work on the hydropower project or any such type of long-term infrastructure, you should instrument it, because you have to measure the that whether there is any movement or not. During construction, if you put some inclinometer here, or you can put some piezometer here, so that we can measure the pore pressure and the stresses, then it is good that we know that this area is in stress. Once you have constructed this, we just cannot put any incline to anything. Okay, so we are helpless. We don't know what to do. So with simple theodolite and electronic distance meter robotic station, we have prepared some benchmark, and from the road level, we are measuring. In fact, now what we have done is that this is the wall, and because wall we cannot disturb. So from 2 meters from the wall, we have put some inclinometer, so that if there is a thrust, there is a pressure underneath due to this wall, it will be reflected in this inclinometer. So that's what we are doing in the instrumentation part. Why I am telling you this, that whenever you come across with such type of structure, you should know that how much thrust or how much stress it can generate, so that you have a buffer zone from the structure. And secondly, that it will be better that during construction only you should plan a good instrumentation plan, good instrumentation program, so that you can tell the public that, okay, when we have this instrumentation, if there is some problem, we will get this data. These days, inclinometer, online inclinometers are there. You have constructed a wall in Sikkim, you can rightly in CBRI Rookie, you can get the data. Okay, so those type of facilities are there. So this type of instrumentation is needed. So we have, as I have told you, that we have put the inclinometer and we have put some altimeter also on the road. So I think with this, I am at the end of my lecture. So the conclusions are: landslide hazard assessment is very crucial for landslide risk management. Spatial prediction of landslide. Now people are talking about early warning. Okay, so before we go to a temporal prediction or early warning, we should at least first know that what are the areas which are potential for landslide. So for that we need a spatial prediction. The spatial prediction means that we have a landslide hazard assessment map. We should know that which area is going to fail. Once we know that these are the area which is going to fail, which are going to create some hazard, then probably we can have a good rainfall monitoring system and can say that, okay, these are the area where landslide can happen. So if we have that's what we are also studying this, so that the rainfall threshold, that okay, if this millimeter of rainfall is there, then in this area we can expect some landslide. So we can have a landslide warning system, or we can warn the people. Historical data, large scale maps are not available. So these are some limitations. So field and laboratory data. So whenever we want to work, we have to create our own data. Okay. Then once the landslide potential is identified, the design of mitigation measures can be taken up to control landslide. And I think the landslide hazard map should be undertaken along all the hill roads. Because see, the remote areas, even if landslide occur, I don't think that there is much we are losing, because people are not there. But where there is inhabitants, there is along the road, which is where particularly during the monsoon season, in good hazard map should be created. Such a study should be okay. And then there are different techniques for slope student analysis. So you have, as I told you that, I have told you a few techniques. So there are many techniques. So before you go for a stability analysis, you have to decide that which stability analysis technique, which software we have to see, so that we can get a better result. So it depends on your objective. It also depends on the data availability. Every time you don't get data. If we see that there is a landslide, I'll say that, okay, I want this data, in situ data. From where I will get this in situ data? We won't get, because very difficult that we take all the machineries to calculate. So at that time, what we can do is that, as I told that, you calculate GSI, RMR. From those data, you can at least estimate certain strength characteristics, so that you can able to calculate the stability analysis, calculate the factor of safety, right? Then in-depth study and investigation required for tangible solution to address the problems arising due to construction activities and field. So this is also a very important part that one should take into consideration. So I think I am done with my presentations. So any questions, any discussions you want, I am there. Or you can also mail me if you want any publication, any yeah. So Dr. Mahesh, I am done with that.
Thank you, sir.
Yeah.
Thank you for a wonderful presentation covering all aspects related to slope stability analysis. So thank you for that. I think now we can have some questions. So participants can also put their questions in the text box, in the chat box, if they have any questions or queries. So we can take it from there. Sir, I also wanted to take your guidance.
Right.
We are presently, my department is presently going to collaborate with the state disaster.
Mahesh, just 1 minute. I want to answer it first. No, I want to get take, let me just, then we can discuss better.
Yes, sir.
Here, not it is coming answer. Let me see.
Okay, so any participant, if you have any question, you can put your question in the chat box.
Yes.
And if required, I also can unmute you. Okay. So, sir, before any question from participant side comes, I wanted to take your guidance, because basically what is happening that we are going to collaborate with the State Disaster Mitigation Authority. I was also discussing with you, I think few days back. So could you please help us, like how shall we go ahead in dealing with this preparation of DPR for landslides? Could you please guide us, like what should be the steps from our side if we are going to collaborate with the State Disaster Mitigation Authority?
Got it. So for preparing a DPR, first you have to, in the DPR you have to see that what type of problem you are facing related to landslide. First thing is that, okay, whether you are facing, you want to do a very site specific hazard study. As I know that you people will be interested for a site specific studies on landslide. So identification of some major landslides and select a road in the Himachal where you are, the road is very busy and road is very important, and how many landslides are there. Then you prepare this DPR that type of investigations you have to carry out. So type of investigation, type of stability analysis, and then finding, and then the remedial measures. So these are the three techniques, three steps. So like that, you can prepare on that, So I don't think there's any problem. You send me this document sort of things. I'll help you how to prepare a DPR, because in the DPR, the very important part is that you have to show the importance of your work, what your project proposal. So you have to define that the road on which you want to work, how busy or how much traffic is there. So, and there are several landslide spots, hot spots are there. So on those spots, you want to do the analysis, stability analysis and remedial measures. So like that.
Okay, thank you, sir. Surely I will be sharing the document with you once prepared from my side. The second question is that there are many different sort of remedial measures that we generally try to incorporate or install in the field. But we have to definitely take into consideration the cost of installation and cost of, yes, sir. So based on your experience of more than 30 years, what can be the best possible solution? Although the solution is always site specific, that is totally understandable. But when we are looking into the landslide mitigation strategy part, like what should be the core course of action from engineer's side, like in terms of the option that he should start from?
So now, that is very easy. That first you see that the debris or soil slope, or it is some kind of rocks. Okay, if it is a debris or soil slope, you have to have design some drainage measures. Okay, this is very essential. So if the soil slope or debris slope is there, you prepare it. You have to have a design of drainage measures and a retaining structure. So mostly in hills, that's what I am telling, hills, it is all gabion wall, you can see. And gabion wall are cheap. But only thing is that those gabion walls should be designed properly. Gabion wall looks like, kisi wo blocks bana diye, net bana diye, and you prepare some wall. It is not like that. You have to, what is the size of the blocks, what is the size of the net, everything you have to design properly. So gabion wall is very cheap. So drainage measure and gabion wall, these are the two things very important. The third is that, as you have worked, your thesis that so the reinforcement part is the third part is very important. So one is the drainage measures, At the toe, you put some straightening structure that is mostly Gabion wall. And if there is a, you can put some nail, So with the soil nail, you can absolutely control any sort of soil and debris slide. I think you have already designed some soil nail, and of course now I think now this is a time that you should think of putting your helical nail somewhere, so that
yes, sir.
So it will give you really, we will be happy that somewhere if we can put helical nails. I think in DPR also you can mention that you take up this project on a nail, different type of nails. So debris slope, and if it is a rock slope, then best part is that try to have that rock catch fences, because there is a difference between a protection measure and remedial measures. Remedial measures means you are controlling the landslide. In the rock fall, instead of remedial measures, protection measures are very important. Rock catch fences, and also you can think of. In fact, I was also interested. You can think of doing some work on the rock sets. That is very gray area now. Nobody has worked in India, at least. You develop some good material and then design a rock sets. Wherever there is a landslide, you try to put a rock set. That is very good. That is very good. And people have not worked in India. I think Shillong Silchar Road, I think Water Road has implemented one rock set. Otherwise, you don't get such type of rock set. These are very good.
Yes, sir. Yes, sir. Thank you very much, sir. I think rock shed is one of the solutions that suits best.
Yeah, but
all of us.
Maybe a little costly. Maybe.
Yes, sir. Yes, sir. You might have seen in the media, I think, few days back, where large chunks of rock fall that happened in Kinnaur, and there were some casualties also.
Yes.
Now this kind of problem is coming up like very much prominently, day by day in Himachal. Otherwise, landslide and slope instability was not that much issue in comparison to Uttarakhand.
Right.
But when this widening of roads started, and I think somewhere definitely human intervention is one of the best prime factors behind that. Now we are suffering from large number of casualties, I think, every month because of some sort of landslide or rock fall or anything associated directly or indirectly to it. So, sir, I think this rock shed is a wonderful idea that can be installed or constructed at least on those areas, on those roads, which are of very much national or strategic importance.
Correct.
I think in India also we don't have much expertise in designing of this. So I think it's a wonderful research topic also for PhD aspirants. They can take it up. Yes, sir. Yes, sir. So apart from, thank you, sir. I think if there is any other question from participant side, we can take it up also.
Yeah, sure.
I received. Yes, sir. Yeah, you please.
Even if the questions come in letter part, in the mind, they can always write to me. My mail.
Right, sir. So, doctor, you can always, dear participants, you can always.
I think there are some question in the chat box. You can see.
Yeah. Yes, sir. Yes, sir. Let me just check. How can we evaluate the factors of safety of landslide? Is there any method to find slip of rock mass at earliest? So this is a question by Mr. Kadir Raza.
How can we calculate the factor of safety of a landslide? Is there any method to find slip of rock mass? Yeah, see, factor of safety calculation, you have to go to soil mechanics. You have the simple thing is the limit equilibrium analysis. So for that, you have to see the book, and there are techniques. So right now, it takes time. But
right.
Stability analysis means a factor of safety. So it is basically a ratio between resisting force and the driving force. Okay, so you have different methods. So if you have the 3-4 things. One is that you should have the slope profile, geometry. Okay, then you should have the shear strength characteristics of the soil material, that is called a C5. Okay, so if you have a C5 and density and the slope material, slope geometry, you can calculate the factor of safety. Okay, stability analysis. So if the stability analysis is 1, in a dry condition, it may be marginal. And if it is 1 in dry, definitely with pseudostatic, this means considering the earthquake conditions or the bed, it is going to, it will go down. So I think if the factor of safety comes between 1.4 in dry, 1.5, I think this is good enough. This is good enough.
Yes, sir.
What
So
are
we all
signals of landslide?
right.
So warning signals of landslide, you can think of that. This is good question, and whenever we go, we always discuss with the villagers that if there is a crack happening in the ground, if there is a distress in the houses, and there is some initial movement, or you can have that that there is a rock, fresh rock, you can see in the slope that there is a falling of, this detachment of a fresh rock, so those areas are it gives a signal that anytime, rock fall can happen. And also for the signal means that you should see, I am more worried about these days about the rock slide, because debris slide and it takes time, but the rock fall, rock slide, they don't give much time, So, you should see the geological discontinuity and the slope, So if there's the discontinuity plane is almost parallel and equal to this slope, then there is a chances of rock slide. So you should see that, and of course there is a chances of toppling failure also for a particularly jointed rock digging in the slide. So those are the things, but actually I should say that it doesn't give much time for a warning of, if it is going to a slow moving slide, then as I told in the Bhatwari that there is a crack occurred on the road and slowly. Those things are, even for Uttarkasi landslide, there are some debris which came down and then people say, okay, there is something going to happen. So they take the initiative. But for a debris flow, like huge in a cloud burst, along the river valley. So debris flow and those rock slide, we don't get much warning. But even if that, one should be cautious. Now people for rock blocks, people are also, if you know the area which is prone to rock slide, you can put some crack meter or tension meter. So if there is some distress, then it gives some siren and you can have warning. I have seen some example from Chinese geological survey. So they have put some track meter along with some sirens. So as soon as there is a generation of stress, that there was a siren and people came out from the house, and there was a huge rock slide, but there was no casualty. Okay.
Yes, sir. So I think there is another question from Mr. Ankit. Is there any early warning that you have already?
Is there any suggestion from you and village mission to follow while doing
construction activities? Yes, sir.
I think this answer can be will be given by Mahesh.
Yes. So I think as sir also suggested, there are many suggestions and many guidelines can be definitely taken up by the masons, but it's very difficult to tell those things to masons. So the idea should be that when they're getting their training, because in the state of Himachal Pradesh, masons are being trained by, as also our chief guest pointed out, by some sort of disaster mitigation authorities. And presently, CBRI officials are playing key role in training those masons, so that all those technical things which we engineers or scientists feel in the laboratory level are being communicated to the mason level. So I think few small things, that how to judge whether there are some sort of major warning signs already shown by some sort of a slope stability in the field, and what kind of weather is there when a machine is going to go for work. For example, the rainy season is going on, and every day 1 or 2 casualties are taking place. So when your sixth sense, I must say that sixth sense or a little bit experience of the field, you try to incorporate into that, then I think those things can be definitely be very much helpful for masons who are working at the village level. And these sort of guidelines can be issued by the concerned officials within the state or NDMA also.
Actually,
Yes.
what is happening that this type of training and all, we are giving it to engineers, PWD, but from there, again, it should be translated to the actual masonry.
Yes, sir. Yes, sir. Yes,
So
sir.
that is important. That is
Yes, sir.
yeah.
And I think we also have one participant who would like to ask question, that is Mr. Sridhara S. Sir, can you hear me? So I can unmute you.
Yes, sir. Yes,
Yeah,
Dr. Mahesh.
please go. Yeah, please go ahead for with your question, sir.
Thank you so much. Thank you very much, sir, for actually enlightening us with this landsliding. And we are blessed to listen to you, having ocean of knowledge, that too in practice and in field. Thank you so much, sir. My question is, sir, regarding this stability analysis and arriving at rock mass rating, because most of the area where landsliding happening is earthquake prone areas, where tectonic plate junctions are there at the Himachal Pradesh area, wherein are we actually, while coming to a factor of safety or assessing rock mass rating, are we considering this seismograph details or acceleration or this seismic related parameters while arriving at this rock mass rating or else stability analysis for minor shaking, just for minor shakings? Thank you, sir. That's what my question.
Sir, I think you are muted.
Yeah. So actually, for rock mass rating, this is a rock mass classification criteria. Okay. So it doesn't really take into account this earthquake and all. Indirectly, but not directly. But when you do the stability analysis in the pseudostatic or dynamic condition, we do take the earthquake acceleration. So there are, if you go to the literature, there are different, factor for different earthquake zone. Okay, say for seismic zone 4, we have a we have to take into account this for horizontal acceleration. I think the zone factor is 0.24. This will be multiplied by the site amplification factor. Now, when we talk about site amplification factor, if we have the the earthquake data or the seismometer from where actual data that can be incorporated, it will give a very good result. Otherwise, we have different zone factor for different earthquake zones. So the vertical and horizontal acceleration data we give and then calculate the factor of safety. That's we call the pseudodynamic state. So this is what.
Yes.
Okay. Thank you so much, sir. Thank you so much.
Yeah. But I tell you that if you see about the tectonic zone, okay, earthquake is important, but when like in 2017 earthquake came and so people are doing like that. So earthquake data even is good if you can calculate with this data, but the main culprit these days for landslide triggering is the rainfall, and second, as Umesh told, is the human interference. See, the slopes are stable, okay, and say is a stable region, so you are not disturbing it. There is no problem. Once you disturb it, you are steepening the slope or you are reducing the strength property. You have to have at least some remedial measure, because once it starts and you don't have any remedial measures, it will be a chronic problem. So we have to tackle the problem right at the beginning. Okay, I am not telling that we should not do any development. You have to do development activity should be there. As soon as you are disturbing the slope, at least quickly you should try to have some remedial measures so that it won't exacerbate the problem.
Yes, sir. And sir, I was just wondering the way we prepare detailed project report when a construction activity is going to start somewhere, or pre-feasibility report. You know, a construction activity that generally takes place. Why not to prepare also a report that if this construction activity takes place,
Yes,
how much slopes or other things are going to get destabilized, and what will
exactly.
be the cost of stabilizing all those things. I think that should
Yes.
be also included in
So,
those reports. Yes, sir.
yes, so that's what I am telling, that whenever you have planning, have a construction, at least you should have a basic hazard map. You know, some of the places where if you even if there is nothing going to happen, but the hazard map means that you are trying to predict a special prediction or that there is a potentiality of landslide. There is no landslide now, but once you disturb the slope, there is a possibility that landslide will occur. So that is what I think, that a basic first-hand landslide hazard map should be prepared before we go for any infrastructure development.
Yes, sir. Yes, sir. So I think we have taken some questions. If yeah, if there is any other question, then you can also definitely write to through mail to Dr. Shantanu Sarkar.
Sure, sure.
Yeah. Thank you very much, sir,
Okay.
for taking out time for this lecture.
Yeah.
Thank you.
Okay.
Okay, sir. So,
Okay. Thank you very much for giving me
thank
the
you.
opportunity. So I am happy
Okay.
to interact with you all.
Yeah.
Yeah.
Thank you, sir. Thank you.
Yeah.
Thank you, sir.
Okay. Thank you.
Okay, sir. Okay.
Okay.
Okay, so dear participants, our next speaker will be joining us from Italy. She's Maria Giovanna. She's a young speaker. We have taken one young speaker also. So one experienced researcher working in the field of disaster mitigation, and then one young researcher. So she will be joining us at 1:15 p.m. from Italy. So if you want to take a break, but I request you not to leave this meeting. You can keep yourself muted and join around 1:10. So at 1:10, we'll be starting the session by 1:13 or 1:14. Okay, so in order to so the all the sessions are, there is no such interruption from internet connectivity. I request you not to leave the meeting and join. If someone has left the meeting, then join by 1:10 p.m. Thank you. If you have any other question or query or suggestion, please you can raise your hand, or also can put it in the attendance box. Yeah, attendance link. I think Anamika Gandhi ji is asking. So what we are exactly doing? We are getting the attendance directly from here. So I think that's the strategy we are right now following. Oh, I think Maria was also the participant in the previous lecture. Thank you. So Maria, we will be listening to you at 1:15 or 1:10 p.m. Thank you very much. Yeah. So if you have any other query regarding attendance or query any other thing, you can always text it in the WhatsApp group also, and put it in there also in the chat box. So I think we can have the break. So you are requested not to leave the meeting. You'll be there in the meeting for next 15-20 minutes. Okay. Thank you very much. So we'll be joining at 1:10 p.m. again. Thank you.
रोज मीटिंग थक गया हूँ साला। आज एमडी पूछता है, कल डायरेक्टर जनरल पूछता है, परसों ये पूछ लेते हैं, फिर एमडी पूछता है। भाई कराने के टाइम तो दो, डेली डेली पूछते ही रह रहे, एडमिशन हो गया, एडमिशन हो गया। अब और भी तो काम है इसके अलावा। विकास से लंच कर लें। हाँ हाँ हाँ। आज ऐसे पोहा बना दिया है, पोहा बनाया तो बेकार से खाऊंगा। बहुत अच्छा दे पाते हैं। पहले तो सबने 12 बजे तक बोला सुबह कर दिया। अब आदमी जब फोन करता है तो क्या करेगा? ऐसे यार तुम उसके बारे में नहीं कुछ भी आज पेपर लो ना, ये लो पेपर है। मैंने बता दिया है ऑनलाइन पे क्लिक करना। तो मैं सोचा नंबर ऑफ डेज पे कंटेंट करेंगे तो नंबर कैसे देंगे, तो पहले कैसे बहुत ही चलेगा। हाँ तो उनका देखो वायर कैसे किसी का साफ से नहीं आएगा। ये तो पता है कि ये क्या है, बैटरी फोन देना लगा के बात हाँ तो बिल्कुल वो बनाया हमने नहीं बनाया, मैं आपको वही बनाया ड्राइंग किया ना और यहाँ का मामूली तो मैं कुछ भी करके देखते हैं आपका भैया आप यहाँ से कैसा हेलो वालेकुम अस्सलाम। अरे वो 90 है। हाँ 90 पे तुमको मिलेगा, कुछ मिल भी जाएगा। तीनों साल 90 ही है। हर चीज अलग अलग है। एक बार को मैं कंफर्म करके 15 मिनट 20 मिनट फोन कर ठीक है आप ठीक है ठीक। बैठो बैठो सर। हाँ हम लोग भी चलेंगे, बैठो। क्यों इधर जा रहे हैं? वैरायटी नहीं मिल रहा है क्या? अरे यार अभी भी वही काम करके आ रहा है। सॉल्यूशन बन गया। अरे कहाँ बनाए भाई, बस पागल चले गए। तेरी नोटिस चल रही है। एक्चुअली लड़की जो था ना, तो हमने 30 में डिस्काउंट करा उसमें वो चाहते थे डी फार्मा डालो। अच्छा, अब हो गया। रजिस्ट्रेशन किया है, तो फीस भी अभी जमा होता है। ऑफिस करते हैं फुल फीस। फुल फीस कर पहले तो उसको मिलेगा 12,000 बच्चे 12,000। बच्चे को फायदा करा रहा है। वैसे बोले नाम है ना, क्या बोलिए, इन लोगों ने नहीं किया है। डाल दो अवश्य कॉपी चेक करो लेकिन बात करना ना बात कर लेते हैं। आपका बेटा कौन सा दूसरा का प्रार्थना दूसरा समुद्र में इसको कैसे दे लेकिन ये लोग को बताया ये बात को करेंगे इनको काम निकलवाना है। नहीं हमें नहीं चाहिए हमारा इसे हमारा सब लिटरली होता पढ़ने को कैसे होता कुछ माइंड होना है तब हम लिखेंगे और करेंगे दिमाग खराब कर अगर हड्डी हर रोज हेलो आज का बोलो। हाँ हाँ एक सबका पर्सनल बनेगा और फुल कॉमन बनेगा। रूल रेगुलेशन देख लो उसमें। दो दो कॉलेज के लिए बनेगी, एक टाइप का बनेगा एक एचओडी ऑफिस के लिए, ठीक है। एचओडी ऑफिस और गाइड के लिए जो रहेगा उसमें सारे बच्चों का नाम रहेगा, ठीक है। अब सुनो एक सब अपने अपने बनाएंगे। तुम्हारे ग्रुप में 5 बच्चे हैं ना, तो 5 प्लस 2 एक्स्ट्रा 7 फाइल है। अच्छा हाँ अब सुनो तो बताओ। नाम होंगे नया डेट से क्या है नहीं भगवान। अगस्त में लेंगे, अगस्त में देख लो, अभी नहीं देखे। अब मैं देख के बताऊंगा, ठीक है। आज तक मैं कर दो बहुत
Good afternoon, everyone. I hope that you have had your lunch, and we'll be starting a session within 5 minutes. So I'm just expecting that all the participants have joined back this workshop. Thank you. Hi, Maria.
Hi, how are you?
Oh, I'm good. I'm good. Thank you for taking out time. I think it's a morning.
Yeah, morning, but not so early. It's it's perfect
Yeah,
time for me.
yeah. Thank you for joining us from Italy.
Yeah, I am very happy to participate to this online conference. Yeah, I would. It would be better if I was in person there.
Yeah, right. Because Italy is also very much a tourist destination, right? And Shimla is also a popular tourist destination for South Asians. Yeah,
Yeah.
and this university is located in Shimla.
Ah,
Yeah, and Shimla was the summer capital of Britishers when Britishers were there in India. They were ruling India. So
yeah.
it has a lot of historical, what you call it, background to it, the way Italy has.
Yeah, and another thing, yeah, it's that University of Salerno and the University of Grenoble Alps, the both universities that I attended during my research career, um, are strictly connected with India. For example, my first foreign student that works both with these two universities is Indian, and now it's at the end of his PhD course. Parul Chauhan.
And you know,
But
so
sorry, now I cannot hear you perfectly.
I think, can you hear me perfectly now, Maria?
Oh,
Yeah. Am I audible to you?
mm, okay, I don't know what.
But you are very much audible to me.
Yeah, I cannot hear you.
I think, can you just
Ah, okay. No, yes.
yeah, I think I messed up with my, what do you call it, my cord here, I think. Yeah. I was just saying that, before joining here, I was in US. So I had 3 or 4 guys from Italy who were doing postdoc in, there in the California only, because I was at University of California. So they were in other campuses. So yeah, so we very much gelled up. Yeah. Okay.
Okay, it's
Yeah. So now you are also presently working in the same university, right?
sorry, the microphone.
Yeah, wait a second. Just it in some another way. Yeah. Hmm? Okay, I will try to adjust in this way. I think
Yeah,
I think this works
yeah,
better. Yeah. So you're right now also working in the same University of Salerno, right?
yeah.
Okay. One of my junior is also, I think she's also presently doing her master's at University of Salerno in the field of architecture from
Ah,
India. Yeah. So we have many people in that university of who are working or doing their research there. So
yeah, and also University of Salerno, and in particular my research group in geotechnical engineering organized 1 year ago, yeah, a Laram school in India,
yeah, right.
Rocky University.
Yeah. I know that. I think I missed that. I was in Roorkee that time only. It was organized by IIT Roorkee in India and along with your university. And yeah, so I'm expecting that maybe in the future my university and your university will be taking it up together.
Yeah, it would be great. Very
Yeah,
good.
right. Great. So I think we can start our session, or we can wait for 1 or 2 more minutes, right?
I don't know. Here I have.
Yeah, I think it's still 1:23 p.m. here, so we can
Yeah.
start at 1:25.
Yeah.
So you are still working in the same area, or you have changed your area of research from your PhD?
Yeah, I little bit moved for the interaction between root and soil. Does again laboratory tests, but I had also field experience.
Okay, so but exactly because I think the researchers at University of California, especially Professor De Jong and Alejandro Martinez are also working in this area where they are trying to, study the properties of root-inspired anchor systems. And I also was very much fortunate enough that I got a few months, not much time, to work with them. But I think this area is something very much attractive, and because it definitely takes into consideration the sustainable point of view, to provide a mitigation measure in a sustainable and efficient way, right?
Yeah, also in Italy, because there are some limits due to landscape and the rules to not to preserve the skyline or the landscape of our place. Thus, sometimes the presence of tree or herbaceous plants, it's perfect to mitigate, to match the two necessity, mitigate landslide risk and keep our landscape, our natural background.
Right. Yeah, because I always wonder that nature, through its evolution, it takes millions or billions of years to finalize or to come up with a solution as a tree to mitigate, prevent landslides, right?
Yeah.
And it's always very much amusing to see how nature think that this should be the angle of, branching angle of roots. This type of, tree would be more efficient for this kind of landscape. So we have many things to learn from nature, and definitely it's on my task to organize one workshop on biogeotechniques, because I think that's the upcoming area of research, and definitely I think all we people need to work into that area so that something more efficient, sustainable can come out as a solid solution oriented approach. Yeah. Right. So I think Maria, we can start your lecture. I can introduce you formally. So dear participants, it's my privilege to introduce a young researcher who has joined us all the way from Italy, and must first of all thank her to take out time from her busy schedule, that also in the first half of Monday morning. Yeah, so she is Dr. Maria Giovanna Moscariello, and I'm sorry if I pronounced it in.
No, it's all right.
Yeah, and she has done her PhD from a prestigious University of Salerno, Italy, and she has been visiting scholar also to University of Grenoble Alpes at France. Before that, she did her master's also from the same institute, University of Salerno, Italy. And as a young researcher, when I see her profile, it's wonderful. She has wonderful international publications, and now she's taking it further. So I welcome you, Maria, and thank you for accepting our invitation. And we look forward for your presentation. Thank you, Maria.
Thank you to you. I want to say good afternoon to Indian people because I think that is afternoon for you. I am sharing my screen now.
Please go ahead. Yeah.
Yeah. Okay. Not this. Okay. Yeah, my research topic is multi-scale laboratory testing and the constitutive modeling of pyroclastic soil involved by rainfall-induced shallow landslide. I can just anticipate one thing, that is pyroclastic soil are typical of my birthplace. Thus, my research started from my birthplace and the place that where I live. And it's important to me because we will see in the next slides also some places that are very close to my house, and thus the landslide and the risk connected to landslide, it's an important topic for me because it's a part of my life. For example, if I saw rainfall, yeah, there is an alert from civil Italian protection that say, okay, don't worry, it's only rainfall, or keep attention, don't go near that zone or the other zone because there is a risk. It's a way to say that this topic, that is laboratory testing and the constitutive model, does in geotechnical engineer could be far from risk mitigation. In real life, it's like to say, okay, laboratory testing and constitutive model are on the base of risk mitigation. And let's go to see the materials that I will show you, that are pyroclastic deposits that comes from eruptive volcanic activity and derived from sedimentation of tephra and the emplacement of pyroclastic density currents. And these deposits are characterized by high spatial variability of physical properties, but some common features can be recognized in my pyroclastic soils. Thus, pyroclastic soils derived from Vesuvius volcano in southern Italy, and the other pyroclastic soils that corresponds to the 1% of soils that are in the world. And these common features are light gray of grains that are due mainly to mineral composition, that is a non-crystalline composition. Thus, we are talking about of glass minerals the high porosity of the deposits, which means that porosity could reach 0.70% in terms of porosity, that is very high. A metastable structure or open internal structure, and the volumetric behavior that is particular because it's dependent on the degree of saturation, thus on the water infiltration, and the pyroclastic deposits are often in partially saturated condition. This part is very important because partially saturation and the variation in terms of degree of saturation can lead to the landslide that are typical of these deposits. But the hazards connected to pyroclastic deposits are not only landslide. In fact, we can imagine a line during the time, and we can say that the hazards can occur both during the eruption with the interruption of air traffic, or the increase of atmospheric powder, or the stability of the structure of the roof of the infrastructure. The hazards can be related also to the period immediately after the eruption, with the LARS, with the volcanic debris flow, that are parts of my topic, and several years after, how we can say for Sarno, there can be catastrophic landslide due to the variation in degree of saturation of pyroclastic deposits. But let's go to see the shallow landslide and the feature of these landslides. These shallow landslides are one of the most common types of landslides that can occur in general in different gradient and origin deposits, but they are most common in pyroclastic deposits and develops on steep slopes that are typical of southern Italy and Campania region landscape. And they often, of course, after or during heavy rainfall, and the main cause is the infiltration of rainfall in pyroclastic deposits. Moreover, in steep pyroclastic deposits can cause very destructive events, like we can see in two movies. One is from Nocera, my birthplace, and the other one is the most famous landslide of Sarno 1998. Let's see the video of these two events. And in the first video, it's from Nocera. And we can see the triggering area and the propagation of this landslide that goes 4 or 5 feet because this mass, the mass that moves from this area go directly against a structure, a building in which one family died, and one family lost their life. And we can see the video that is recorded immediately after the landslide. Thus, we can see that there is a triggering area in a hill slope that is completely vegetated. It seems an healthy relief, not there is no signal that can occur a landslide before. We can just see the triggering area, the part in which the mass is in movement, and the deposition area at the toe of the relief, Montalbino relief. But let's start to see also the video about Sarno area. I don't know if you can also see
that same year on the
hear the voice of this video. Please let me.
Yeah,
other side of the world,
perfectly audible. Thank
a much larger mudslide killed hundreds in the Italian town of Sarno. Just after 7 a.m. on May 8, 1998, a giant 10-foot wall of mud descended upon the unsuspecting villagers. For more than 15 hours, frantic townspeople joined authorities to search for survivors and rescue trapped victims. More than 600 people were buried alive as they slept. Many of the bodies will never be recovered. The hardening clay has become a permanent tomb for many of the town's dead.
There really is no precaution a person can take to prepare for gigantic mud flows. If one is coming to town, its effects are so complete, the only practical course is evacuation.
But many experts believe that the tragedy at Sarno could have been avoided. The town was built on a hazardous layer of clay and chalk, common terrain in the mountains surrounding Naples. When saturated, this soil combination becomes extremely weak and crumbles.
These mountains are notoriously unstable and can produce devastating mud flows that can travel miles down slope.
Experts warn that the climactic conditions that created the catastrophe at Sarno are not at all uncommon, and that thousands, perhaps millions, could be left homeless or even killed the next time nature goes totally out of control.
Okay, here there is just one thing that it's important to say. It's not only a mud flow. It's a shallow landslide, very complex, in which there is a mud flow, debris avalanche, and debris flow. Thus, it's a little bit too complex that is explained in this video. For this reason, there were many studies immediately after the event of Sarno, and 6 typical triggering mechanisms are identified in this area. As we can see, the mechanisms are related to water infiltration, as we can see in M1. It can be due to temporary spring from bedrock or rainfall in M1. In M2 and M3, we can see, in M2 and M4, 5 and 6, we can see that also morphological feature of the area can influence the triggering mechanism. And in M3, we can see also that morphological features are not enough, but also human activity can influence the triggering mechanisms. Thus, 6 triggering mechanisms are identified, but it's also it was also identified the most common mechanism, that is M1, in which the role of water is predominant, and I focused my research topic on this mechanism, and in particular on the main difference between saturated and unsaturated soil behavior. Let's start from the first differences. The first differences are that volumetric behavior of soil in a saturated condition, it's mainly due to a variation of volumetric water content. Instead, in unsaturated soil or partially saturated soils, the volumetric soil variation, the volumetric strain, are not strictly or not only related to changes in terms of volumetric water content, because unsaturated specimens or unsaturated deposits can exhibit volumetric deformation due to a changes in terms of stress variation or in changes in terms of suction. Especially, let's start with another movie that can explain better than me the effect of water in terms of shear strength in an unsaturated soil. So I asked to help me Professor Barland to better explain the effect of water on soil strength.
We've already seen that soil is a particulate material, and one of the really interesting features of particulate materials is the voids that are between the particles. Now, depending on where the soil is, it can be either filled with air or with water, or a mixture of both. Now, in this video, I want to show you how important water pressure is in determining the behavior of the soil. In my experience, major disasters can take place if the geotechnical engineer does not understand the importance of water pressure. For example, the Aberfan disaster in 1966, where water pressures were allowed to build up in a man-made soil on the hillside above the village of Aberfan. Eventually, the soil mass slid down the hillside as a slurry, killing 116 children and 28 adults. Now, in this demonstration, I want to show how important the water pressure is at the contact points between two particles. Now, I've got two particles here. You're going to have to bear with me, but one particle is this melamine board, if you can imagine that, and the other particle is a beaker, and here it is, and this beaker is full of water. And we place this beaker full of water on that surface, and you'll see that it is stable. Shearing resistance between the cup and the board is great enough to stop the cup from sliding downwards. Now let's look at an identical beaker. Here we are. We'll place it on that slope and we'll fill it with water. And we'll observe what happens. We'll see that that slides. We'll do it again. Now, why is that? Why should one beaker be stable and the other not? And the answer is that this beaker has a hole in the bottom. Now, the implications of that are that the water seeps through that hole and the head of water generates a pressure between the beaker and the wet surface. The pressure that builds up causes the force between the beaker and the surface to reduce. Now, we know from the laws of physics that if you reduce the contact force between two frictional surfaces, you reduce the shearing resistance. And that is exactly what happens here. So we see from this demonstration how a build-up of water pressure between two particles can reduce the shearing resistance between those two particles. Many of you will have carried out experiments building sandcastles on beaches, and you will understand some of the things that can happen to them under various conditions. We're going to build 3 sandcastles. The first one is using dry sand. And we see it forms a cone here. The next one is with damp sand.
Damp sand, it means partially saturated soil.
Now here's
or
another one,
saturated soil.
which is also from damp sand. But what happens when the tide comes in? So let's see what happens. You see, this lovely stable sandcastle has just slumped. Now this effect and this effect we've covered already. Here we've just got the sand grains under their own weight acting frictionally. Here we've seen how water coming in below can reduce the forces between the particles, therefore reduce the shearing resistance, and the sandcastle slumps. Why is this one so stable? And to understand that, we need to introduce a new concept, which is surface tension. Between each grain of sand, there is a little blob of water, and the surface tension pulls the 2 grains together and generates forces between them. And that increases their shear strength. And that is why this performs so well. So in summary, we have seen that water pressure in the voids of a soil reduces its shear strength, whereas in a damp soil, the surface tension in the water between the grains increases the forces between them and increases the shear strength.
So let's start to see the feature.
Hello everybody. Today's lecture is going to talk about one of the most important principles.
Let's start to see the main feature of unsaturated soil and the main difference between saturated and unsaturated condition. In terms of net stress variation, we can see that if we perform a odometric test on a saturated and an unsaturated soil, we can see that the suction can modify the value of yielding stress on the pre-compression stress and can modify the height of this curve, but cannot modify the slope of the virgin line. In terms of behavior, we can say that the specific volume and the degree of saturation plays an important effect when the soil is in unsaturated condition, and the net stress variation, and in particular the increase of net stress can lead to the collapse of the specimen in edometric condition, but only the increase of net stress can lead to collapse, because in unsaturated condition also suction variation, and in particular the reduction of suction, it means the increase of pore water pressure that move from towards a more positive value. It starts from a negative value in terms of suction, because matrix suction, it's a difference between pressure air in the pores and the pore water pressure, as we can see in on this axis, and the suction decrease can lead to the collapse, and it's the suction decrease to zero, or the movement of pore water pressure from a negative value to a positive value can lead to the occurrence of two phenomena. Swelling, that is more common, and we can imagine better a swelling of soil because it can be observed during excavation, or it can be lead to a collapse. Collapse is one of the triggering mechanisms of the landslide that we saw in previous slides. Is together with the liquefaction that occurs instead in saturated soil, but the occurrence of collapse and liquefaction is strictly connected to the structure of the soil, especially the open metastable structure typical of pyroclastic soil is a triggering for collapse. In particular, it was so in the literature that the high porosity and the open metastable structure can define a soil collapsible, so prone to collapse. But let's start to see what happened when we are playing with suction. We see this using the stress path experience poked edometer by Delage, and he showed the stress path in terms of three physical variables. Net vertical stress, it means total vertical stress minus pore air pressure, suction, and void ratio. This three-dimensional space can be also replaced by another three-dimensional space in which the net vertical stress and the suction are kept as X and Y axis, but the zeta axis can be replaced by degree of saturation. Degree of saturation that is strictly related to both water content and porosity, and can be more expressive than the void ratio. But for our purposes, it's enough to see the stress path in terms of void ratio, net vertical stress, and suction. When we talk about drying path, so it means increase of suction, we can see that the soil behavior can pass through two steps. When the suction is before the air entry value, the soil can be considered saturated, and the variation in suction means exhibit the same effect of variation in terms of net vertical stress. When we pass through the air entry value, the soil became to be unsaturated, and a suction variation can lead to a variation in terms of void ratio. But for landslide and for our proposal, we are interested only to this part of the three-dimensional surface, the collapse under wetting. Just one thing before starting with my research topic. We are seeing a three-dimensional surface that is that came out from odometric test. In this case, we are just imagining to reproduce the odometric conditions that are far from in situ experience. In my PhD thesis and my research topic as postdoc, I studied the, sorry, I just want to move this downstairs. Okay, I just want to say that my research topic is study the collapse due to wetting at several scales, because if we came back to the video of Professor Barland, he talked about the forces due to water, due to the presence of water inside the void that are into the soil specimen. Thus, from Barland video, we can also say that the three phases that are into an unsaturated specimen and the amount of and the percentage of each phase can determine the behavior of this specimen. But in the Barland video, there is also a reference to the forces that are generated by water, that are the surface tension between two grains. Thus, to better understand the collapse, it's necessary a study at several scales. Thus, we can start in this presentation, and you can find this scale, this scheme also in my PhD thesis. That is a study of collapse from micro scale from micro scale to macro scale, and it is led through the use of unconventional technique, unconventional device, and more advanced constitutive modeling. How we can see in this first part of the presentation, the introduction to my research topic, we are passing forward the landscape, the area vasta problem that is a landslide, a very destructive kind of landslide, of a quick landslide, to the study of the phenomena at grain scale. It means that laboratory testing and the mitigation of risk, or the design of a structure that can mitigate this risk, are strictly connected. Thus, this topic can be seen as the one or two faces of the same problem, the same issue. Let's start with the study of collapse mechanism at microscale. In literature, there are some more experience in terms of micro-scale analysis of the pyroclastic soils or of the collapse. But these studies are performed using the extractive technique, like SEM images that are obtained from the electric microscope, or mercury porosimeter intrusion. Intrusion of mercury inside a specimen. These techniques are destructive, and they can be performed just before or immediately after the collapse. Instead, it's important to see how the structure of a specimen is modified by a wetting process, imbibition process. But up to now, there are some few investigation on this field, and I will show you one of these that I performed in my research activity. Yeah, at a REV scale, there are many investigation and many laboratory programs that are performed worldwide on collapsible soil. We can see a list that of the most famous papers that are written on this this topic. And in particular, if we focused on the pyroclastic soils of southern Italy, it means Vesuvius activity, southern Italy, or Pozzolana of Naples, that is close to Sarno and close to Nocera, and Colli Albani, that is a complex of relief that are near Campania region. We can see that the shear strength increase with suction, that the soil in unsaturated condition exhibit dilative behavior, dilative volumetric behavior at low stress, while in saturated condition they exhibit a contractive behavior, and that this soil in field condition, in undisturbed specimen, the wetting induced collapse can be observed. As well, can be observed the static liquefaction in a saturated, undrained condition. But if we see to the kind of tests performed in this list, in this table, we can see that we are using triaxial equipment edometric equipment, and also the wetting tests that we can see here are performed using suction controlled edometer or suction controlled triaxial equipments. It means that we are using conventional mechanism of failure or conventional stress path that can be far from in situ condition. Thus, one challenge of my research activity was pass from conventional stress path to unconventional stress path. And we can see in the next slide how and which equipment is used to pass from this conventional stress path to a stress path that is more realistic. But let's see from the material investigated, that is class A, pyroclastic soil, it means a nashy soil. Thus, we are talking about the finer soils that usually are observed in the first 1-2 meters of pyroclastic deposits that are investigated using conventional and unconventional equipment to obtain a soil water retention curve. Here we can see the results obtained from the suction volume extractor that is commonly used to obtain soil water retention curves that are connect, put in a relation volumetric water content or degree of saturation with suction. And this curve is fundamental to the understanding of soil behavior in unsaturated condition. As we briefly saw when we saw the slide about the main difference between saturated and unsaturated condition. Also, the soil water retention curve was obtained through wetting tests in simple shear condition, and we will see simple shear condition is a more realistic stress path than that one that we can apply in volume extractor or in a edometric device. And before starting to my research activity, I collected from Bilotta et al. And from other papers the shear strength failure envelope and the failure envelopes obtained through direct shear tests in saturated and unsaturated condition, triaxial tests in saturated condition, and simple shear tests in saturated and unsaturated condition. As we can see in this image, in this plot, we can see that the failure envelope is quite different and could depends on the shearing mechanism, because we know that direct shear, it means that we are imposing the failure surface. Triaxial tests, we know that the intermediate and the lower principal stress are equals, and in a simple shear tests we will see that it's quite different, the stress path, and it is not possible to describe this stress path using the more plane, because one tension is unknown. And let's start from the unconventional technique that are used for grain scale. It means the unconventional technique that is used for microscale investigation of collapse. We are talking about X-ray images, X-ray computed tomography, that provides some information about the internal structure of a specimen, and these information are kept in a non-destructive way. As we can see in these 3 videos, we are talking about an X-ray source that pass the specimen, and the specimen attenuate the X-ray, and produced on the X-ray detector an imaging that you can see in this video. And this equipment working like a medical device that we used for investigate the state of our skeleton. Thus, in this part of my research, I joined the geotechnical knowledge with the physical knowledge of X-ray and the potentiality of X-ray, obtaining some images of internal structure of a specimen at different suction value. It means at a different degree of saturation. These tests are performed on pyroclastic soils and are performed on 2 pyroclastic sands. So it means that the soil are sieved, and 2 fractions of pyroclastic soils are selected. Why I did this advanced test only on 2 fractions of soil? Yeah, there are some technical problems related to the resolution of X-ray, because how we can see in this video, we are talking about an X-ray source, this red equipment, that is very close to the specimen that is in this cell, in a plastic, a very special plastic material. The cell is a very plastic special material because it must reduce the attenuation coefficient to reproduce the more realistic images, as we can see in these photos, in this radiograph that I put here, and are very close. But how we can see in this photo, the distance between the source and the specimen influence the resolution of the image. Thus, I wanted a high resolution image of internal structure of my soil, and I want to stay with my X-ray source very close to the soil in order to reach my goal. It means see how the grains moves towards the specimen during a wetting process. Wetting that is imposed from the base of the specimen. But let's see how. Just we'll move to this part. Okay. Preparation of specimen inside a cabin that we saw in the videos, in which there is a source, a detector, and an equipment that is composed from a cell in which there is the specimen, a tank that imposes the suction at the bottom of my specimen, and I acquired some images. One, it's at the very beginning of the test, when I just prepared my specimen. Others are obtained after the application of suction, and the suction equalization that occurs in half a day. And I acquired again another 3D image. And then I move to the step application of suction and the suction equalization. I repeat this procedure up to reach the collapse. Then, when I had these images that are radiography that we know in a medical field, I reconstructed these images. I clean from the noise that are typical of X-ray radiography. I obtain an histogram in that we can imagine, or we can compare with the same histogram that we can see in a smartphone app for image processing, just something like Photoshop, just to keep in mind something of familiar. And after obtaining this histogram and after recognizing some peak in my function that can be seen as a sum of normal distribution function, I segmented the images. It means I pass from this histogram that contain the whole gray values from 0 to 2048 gray values, from an images with just 3 gray values. It means with black that corresponds to air phase, air that is around the specimen and inside the specimen, water phase that is this light gray, and the lighter lighter gray or white that corresponds to grain or solid phase. Knowing the amount or the number of pixels that or voxel, if we're talking about 3D images, I can know also the volume of each phase, and so I can estimate porosity, volumetric water content, and degree of saturation just using this histogram to obtain porosity, this geotechnical information, this physical information at global scale. It means that I processing the 3D images of my specimen upon wetting, and then I obtain the information about the global porosity, the global water content, and the global degree of saturation of my specimen upon collapse. This segmentation is a complex procedure that passes through different steps that are not the goal of my presentation, but I just put here in this slide some references that I invite you to see on Google Scholar, on Scopus. And this procedure is, and this slide is just to say that we pass from this histogram to and this image, this real image, to the segmented image. This segmented image, sorry if I go directly to this slide, allow us to obtain this value N3 and SR3. It means the porosity evaluated through trinarized images, and these values are compared with the standard measurement of porosity and degree of saturation, performed step by step, knowing the weight of the soil, the dry soil, the weight of the specimen during the tests, and so on, with the standard technique. Comparing this value, thus standard measurement with trinarized measurement, we found a good agreement. That is an important point, because at this point we can say that, okay, standard and the trinarization images and the trinarization measurements can give me the right information or the same information. Thus, I can use the trinarized images or the images, the measurement obtained from the image processing to pass at a local measurement of porosity and the degree of saturation. But before seeing the local measurement, let's see how the internal structure of soil can be modified by an increase of water content. We start from a high porosity. We can see here that is more than 60%. And this high porosity corresponds to a specimen composed on aggregates of soil and water, in which the water create a sort of bridge between the grains and between the aggregates, and some macrovoids that surrounded our aggregates. Increasing the water content, so increasing this gray, dark gray in our radiograph, we can see that there is no substantial changes in terms of internal structure. There is just more water than the previous images. Then we pass to increase again the water content, and we reach the collapse that led to a rearrangement of internal structure, in which the aggregates disappears, but are again some macrovoids, and we saw from these images that the rearrangement of specimen occurs, and the collapse of the specimen occurs when the specimen is not fully saturated, because there is again some dark areas. That means that there is air inside the specimen. There are voids inside the specimen. This behavior, volumetric behavior, a rearrangement of the internal structure due to the increase of water, it's an expected volumetric behavior for the sand or for the pyroclastic soil. So it's a confirmation of what we are expecting or we are imagining that occurs in an odometric test or in a weighting test on unsaturated specimen. But if we change the grain size of our specimen and we pass to a most finer sand, a more finer sand, sorry, a finer sand, we can see that at the beginning there is again a structure composed of macrovoids and aggregates. But if we increase the water content, the capillary forces rearrange the internal structure. Here we can see that passing from this structure to this one, we observe a sort of shrinkage, and the grains now are closer than the previous configuration, because the capillary forces produced an increase of water bridges, of number of water bridges, and it leads to a radial strain that completely disappears when we arrived to collapse. When we reach the collapse, there is again a rearrangement of the internal structure of the specimen. And we can also observe again that there are some voids. The specimen is not yet fully saturated, but this specimen of fine sand experienced two rearrangement of internal structure. One due to the capillary forces that experienced an increase during the wetting process, and another rearrangement due to the rupture of capillary bridges or water bridges, thus a reduction of capillary forces. And in this moment when the collapse occurs, there is the predominance of body forces that led at this configuration that seems more stable than this one and the first one configuration of internal structure of the soil. But if we saw only to this graph and we compared this graph with that one of coarse sand, we can see that there is nothing that suggests us that can occur these two rearrangements of internal structure. Thus, we must pass from the global measurement of porosity and the degree of saturation of the entire specimen to local measurement. Local measurement that are due using sub-volume, so dividing the specimen in small volumes with different size. And the next step of my research, the following step of my research topic was starting from trinarized images, thus from the evaluation of porosity and degree saturation in a non-destructive way of the global soil specimen to an estimation of porosity and degree saturation at local scale inside the specimen. We are talking about from to measure initially the porosity of a cylindrical specimen of 1 centimeter to measure the porosity in a sub-volume of a specimen of the diameter and the height of 1 centimeter to a sub-volume of a few millimeters. And I start from one micron or 205 micron to reach 200 voxel. It means 1.5 per 1.5 per 1.5 millimeter cubic as a size of optimum subvolume size. When I say that is the optimum, when it's stable, this curve or these curves that are obtaining, measuring the porosity or the degree of saturation on some subsize volume, subvolume that are centered in the center of my specimen. Center of a specimen that, I repeat again, is height 1 centimeter and has a diameter of 1 centimeter. We are talking of the very micro scale, but this micro scale can allow me seeing what happened and which is the mechanism that led to collapse, wetting-induced collapse. Wetting-induced collapse, that is one of the triggering factor of the landslide that we saw at the very beginning of this presentation. This is due for both fine and coarse sand. We saw for coarse and we are seeing for finer sand. And we can see in conclusion that the grain size distribution influenced significantly the behavior of unsaturated sand upon wetting. The increase of water content caused the increase of number of capillary bridges and clusters. Thus, there are two forces that are present in the wetting process. Capillary forces and body forces, and that capillary forces are predominant during the wetting, but at the collapse, the predominant forces are the body forces. Let's see what happened at the Rive scale. So, let's go to investigate the specimens that are more familiar to us, that are, as I said before, investigated usually adopting standard equipment or standard equipment adapted to unsaturated soils. In particular, I used, as I said before, a more realistic equipment that is called suction controlled simple shear test. So, move from France and from University of Grenoble-Alpes, that is the structure that allows me to perform X-ray tests, to my home, University of Salerno. In fact, I used a simple shear equipment designed by Professor Sorbino and Professor Engineer Vito Foresta. That is a simple shear equipment for unsaturated soil. And this specimen, this equipment is particularly suitable to reproduce the in situ condition of steep slopes. And it's composed of a shearing box that is cylindrical. The specimen is cylindrical. At the bottom there is a high entry ceramic disc. On the bottom there is another high entry porous disc, and the shearing box is composed by hollow discs. 12 hollow discs that allow to impress to the specimen a simple shear condition. It means that the only strain that is not equal to zero is the shear strain. Let's start to see the specimen that I used. How I said at the very beginning of this presentation, the pyroclastic soil exhibits high spatial variability. To reduce this spatial variability of physical properties, I decided to use remolded specimen. Thus, as we can see in this brief description, I use the specimen that are created through a standard procedure with a no water content in weight that is consolidated at a no stress, total vertical stress, and is de-aered for 1 day just to be easy to manage and to sampler. The first tests are performed just to identify the shear strength envelope. Some tests are more recent and are shearing stress performed in unsaturated condition. These tests that we can see with a continuous line are then compared with this one that in saturated condition that are identified with dashed line. As we can see from these planes, they exhibit a dilative volumetric behavior. The unsaturated tests exhibit a dilative behavior, while saturated tests exhibit a contractive behavior. This is expected from the literature that I showed you in the very beginning of this lesson. But for these tests, I also take into account the plane of soil water retention curve, and I saw the evolution of volumetric water content upon sharing, and I saw that it's close to the curve fitting obtained through the Van Genuchten model that is used as an interpolation equation of experimental data related to soil water retention curve in simple shear condition. We also saw two other curves in light gray. That curves are obtained as lower and upper bound of the parameters used to interpolate the experimental data. Yeah, the next step of my research activity would be performing more than one curve to obtain soil water retention parameters, but up to now, we use the statistical process to identify these two bounds. But after this, I focused my research activity on the wetting tests, and the experimental program was designed to reproduce the in situ condition. Thus, we start to define a geotechnical scheme of my slope, an infinite slope in a three-dimensional condition, Then we talked about pyroclastic deposits, and we are talking about the flank of a toe. Thus, I need to define a range of slope angles for my slope, and I used the data derived from morphological studies. I also used the data about the thickness of pyroclastic deposits, and I identified with this dashed line and this other dashed line an area of interest in net vertical stress versus shear stress plane to perform my wetting test. S, the area labeled with S, it means that is the area in which are defined my net vertical stress and my shear stress that I would use to perform wetting tests. But wetting tests are also performed reducing the suction with a suction rate. Thus, the suction rate was defining using the numerical investigation performed by Cuomo et al. In 2010. So, my tests are performing, measuring the initial suction of my remolded specimen. Then was a target suction, and the equalization of a target suction was performed. Then was applied a net vertical stress that is inside the S area, and the tau was increased up to reach a target value that is again inside the S area. After that, the suction was decreased. How it was decreased? Applying a suction rate constant or as a function of time, and applying this suction rate from the bottom or from the top of the specimen. Followed the ceramic discs that we saw in the slide in which I briefly presented the simple shear equipment. And what we saw? We saw that there are three different behaviors, because in all these specimens reach at least one failure envelope criterion. One of these failure envelope criteria, it means one of the failure envelope reaching using a different shearing mode, shearing mechanism. But only one specimen reached the failure, and only in one specimen we can observe an heavy increase of shear strain and axial strain. So let's start to analyze the different behavior. Contractive behavior connected to negligible shear strain. The first one, it means that the volumetric water content didn't reach in any moment the curve fitting. So there is a contractive behavior but not associated to failure. Then in this 0,6 specimen, we have no we have just a tendency to move from contractive behavior to dilative behavior connected to moderate shear strain and the failure occurrence at low suction. But this failure doesn't lead to an increase of shear strain or axial strain. If we saw to the plane of soil water retention curve, we see that the path, the volumetric path, is far from the soil water retention curve. But if we move to this test in which we observe the increase of shear strain and axial strain, we see that the water content move through the curve of soil water retention curve and passed it. Thus, there is a strict connection between the volumetric water content, the soil behavior upon shearing and wetting, and the shear strength. Moreover, here we are comparing just the tests performing reducing the suction from the bottom at 0.5 kPa per hour, thus at a fixed shear suction rate. Go to compare the tests performed imposing the suction rate from the top, from the bottom, and with different suction rate values. This we saw before. From the bottom, we have a tendency to move to a contractive behavior, but we did see we see the failure, but this failure is not associated to an increase of shear strain and axial strain. Then we pass to impose the suction rate from the top, that is close to the condition that we observe during a rainfall in field, and we saw that 0.5 kPa per hour led to the failure when the specimen, when the stress path reached the failure envelope. This failure is associated to an increase of shear strain and axial strain, and this increase is evident in this plane, that is the plane of effective vertical stress versus degree of saturation. This behavior is also observed when we apply the suction rate from the top to bottom. Thus, we are talking about a rainfall event, and if we use a suction rate, a suction rate that is a function of time. Again, we saw another a series of tests. Someone we already described in previous slide, but here we see that we reach the failure envelope, and we observe the failure and the increase of suction rate. But if we increase the suction rate, the failure can be observed before reaching any failure envelope. Thus, to predict the presence of failure or an increase is a quick increase because it occurs very quickly, this increase of shear strain, we must connect the shear stress tau over sigma prime with the shear strength and the suction, in particular the suction rate. Thus, if we apply or if we increase quickly the water content, we reach the failure before reaching the failure envelope. This is particularly important if we consider that suction rate is strictly connected to the intensity of rainfall, and the shear envelope is strictly connected to the slope stability. Thus, again, we are studying at macro scale, at rev scale, the phenomena, but we are taking information on the mechanisms that are on the base of landslide occurrence. Here we have some conclusion that I just anticipate in each slide. And now we can move to modulate this behavior. In my research topic, I modulated the behavior using advanced constitutive model. The first advanced constitutive model that I used is the modified Pastor-Zinkevich model that is based on generalized plasticity, in which the state parameters is fundamental, because state parameter, the difference between void ratio at initial void ratio and void ratio to critical state at that effective mean stress, described the difference between the current state and the critical state of a specimen. Thus, describe how far is the specimen from the critical state, and allow us to define a unique set of parameters to describe the behavior of a particular soil, in my case pyroclastic soil, upon different shearing and wetting conditions. I started from this model and I reached the calibration of this model through several testing laboratory testing dataset, but not a large amount of laboratory tests. It's about 37 laboratory tests performed with different equipment, but maybe we can reach the same results using a smaller data set, and we can use this constitutive model and implement this constitutive model to describe the evolution of a large area phenomena on a large area constituted of pyroclastic deposits. And how we can see here, we see that the laboratory tests are easy, are standard laboratory tests. Thus, we left on a side at the moment unconventional equipment and unconventional technique, and we saw that the soil behavior in terms of shear or strain path and volumetric path is adequately reproduced from this laboratory test, both in saturated and unsaturated conditions. Here in this slide, we are seeing how calibrate the parameters related to unsaturated condition. but the modified pastor Zinkevich model allow simulating the saturated and unsaturated condition together, and allow us to simulate also the wetting path using different equipment, as I showed in this paper Cuomo et al. 270. Just to evaluate the performance of this model, I just add an error function that I put here, and is used also for the estimation of the performance of other models. And we can see that this model can adequately reproduce the magnitude of collapse, of volumetric strain at collapse, but it's not so accurate to reproduce the path. But if we consider a large area problem, maybe we are just interested to the end of the process. So the collapse when occur and at which volumetric strain occurs. And we can see that the error it's less than 10%. Thus also these final points are close to real value. Here we can see some conclusion. And just one thing, this part was performed with the Universidad Politécnica de Madrid in cooperation with the Universidad Politécnica de Madrid and of course University of Salerno. And let's move to a constitutive model that is obtained by Muscarnera, modifying the CAM-clay model to simulate simple shear condition. Here, the work is in cooperation with Northwest University and of course the University of Salerno. And the calibration was already performed using a dataset of experimental tests. It's a little bit smaller, this dataset, than that one used for Pastor Zinkevich model. But here it's only focused on simple shear condition and wetting the test in simple shear condition. Thus, we are talking about on an aspect that that cannot be reproduced with modified Pastor Zinkevich model, but it's limited in this study only to simple shear condition. Thus, it's the stress path is almost limited. Then the Pastor Zinkevich model that is enlarged to edometric condition, triaxial condition, wetting performed with a suction rate or wetting performed using flooding technique. But here I had just one more step. Thus, I used a limited data set, but I identified some confidence levels, some values that in which each parameters can be comprised. Thus was performing a sensitive analysis, and I used again the objective and the quantitative estimate equation that we see again here. So I defined the error for each test using each value that is in this table, and I reached some conclusion. The first one, that it's not possible to define a unique set of parameters, like of course for model for Pastor-Zinkewicz, modified Pastor-Zinkewicz model, but and especially that here the friction angle play an important role in the determination of the parameter, the model parameters. But I reached also the conclusion that even if I used the boundary value, so that's that one which has a lower confidence level, I can obtain a simulation or a modelation of the tests that are close to experimental reality, as we can see in these images. Thus, I can conclude that the variability of soil physical properties influenced the model prediction, especially for Buscarnera model, and that the calibration procedure stresses that it's possible to identify a range of variation of a single set of parameters at which can be associated the same confidence level. Moreover, the sensibility analysis performed on parameters related to shear strength, dilatancy, and soil water retention curve showed that the parameters related to shear strength exhibit a stronger influence on the model prediction than others. And the model can be improved, the performance of the model can be improved using an optimization algorithm. This conclusion, it's not a permanent conclusion, because there are so many studies and a paper in submission that shows how this algorithm can be improved the model performance. Thus, also these future analyses are in course, are starting and are performing. But we are talking about the constitutive model at macro scale. My cooperation with the Grenoble and the University of Grenoble led also to the simulation of the tests performed at the micro scale, using a model that can reproduce at macro scale the weighting process. Here I just showed you some images and some output of the model that can show us how it was modeled, the weighting tests that I performed on fine and coarse sand using X-ray CT and image processing. I just put this slide to see you that also at micro scale it's possible modeling the collapse, and that it's possible to define some preference way of the water inside the specimen and how to model this preference way. But it's out of the topic of the conference and of this presentation, explain in terms of geomechanics terms the collapse. Thus, it's just to say, okay, there is the choice to see the collapse in terms of micro scale, in terms of laboratory testing using unconventional technique and using numerical modeling. The study performed on pyroclastic soil of southern Italy was also performed for a volcano in Chile, Cordon Cauce volcano in Chile. But it was associated, the experimental tests performed in the suction controlled direct shear test, with a triggers model, a model that can simulate simulate the large area problem, and in particular can identify the triggering area of a wetting-induced landslide. Maybe someone knows triggers or Shallstab for triggering area, to identify the triggering area. But also this join between laboratory testing and slope stability at large area is also performed for Vulcano Island. Thus, the knowledge on pyroclastic soil of southern Italy, and in particular Campania region, was enlarged to pyroclastic soils and volcanic soils all around the world. But this experience was also enlarged to other slope instability issues, like driver embankments of River Secchia, in cooperation with the University of Bologna. The previous one were in cooperation with the Université de Genève. But came back to river embankment, instability of river embankment, and before studying the stability of this system of river embankment, were performed some laboratory testing, advanced laboratory testing, in which were identified the soil water retention curve, so the water behavior, the hydromechanical behavior of the soil through edometric, suction controlled edometric equipment and direct shear tests. Now, I conclude my presentation, and I want to say thank you to University of Salerno, and in particular to Professor Sabatino Como and Engineer Vito Foresta, to the people that works with me, to the in some cooperation in presence or online, in presence like for Simone Salanger and Bruno Chalier and Chao Wang from University Grenoble, Manuel Pastor and Diego Mazzaran, Universidad Politécnica de Madrid, and I want to say thank you to the other people like Valerie Baumann, Costanza Bonadonna, Guido Gottardi, Carmine Gragnano, and Professor Buscanera and Yanni Chen for online and in presence collaboration. And thank you to you for your kind attention.
Thank you. Thank you very much, Dr. Maria, for... Yeah.
Okay, now I can see you.
Yeah. So it was a wonderful presentation where you gave a brief, not a brief, but very extensive overview of your PhD work, postdoc work, right?
Yeah.
So I think now we are open to questions. question and answer session. And I think any participant can put their query in the chat box, or they can also raise their hand.
Okay, I have some. Okay, some thank you, Madam. Okay, thank you. So,
yeah.
Yeah, I don't know if.
Yeah. So I think maybe they are in the process of coming up with the questions. So before they come, Maria, I think your problem of research was something exciting, where it was something sort of related to volcanic, some sort of volcanic sort of strata was there, right? And I was seeing that slide where that flow was taking place. So in the field, when we talk about engineers who are working in the field, what sort of remedial measures they are taking into consideration to mitigate these kind of debris flows?
Yeah, okay. Let's start to say that I just presented laboratory testing and constitutive modeling because it's the base, because the output of laboratory test and the output of constitutive modeling are then the base, the input for limited equilibrium method or finite element methods that are used to investigate slope stability. And when we reach some output in terms of slope stability, in terms of identifying triggering area, identify the positional area, we can move through the mitigation of risk. Thus, we can move from the engineering choice in terms of retention structure, retention wall, or in terms of bioengineering. In fact, my future was in bioengineering choice, bioengineering structure. Thus, I prefer to say you, okay, this is the start. I found the input to identify the area with the large risk. Then on this area, we must choose the right mitigation system that could be easy, like to define, for example, a threshold of rainfall events or rainfall intensity, and define an alert system for people saying, okay, there is an alert, a meteo alert, and we must move from high area, or we must move from dry area, or in another way, we must design a barrier, or we must define a retention wall, but we must know which volume of soil can hit this area. And we must do this using an approach, a model. It can be the triggers for triggering area, the shell stub for triggering area, but can be the SPH of University of Madrid for triggering area, to follow the path of this landslide, or this quick landslide, because I deal with quick landslide, shallow landslide, flow landslide. Thus, I must define the area or the channel in which there we can find this mass that can be considered a mass of soil or a mix of soil and water. Thus, it's a little bit complex in the second case, because we have something that is like water has the behavior in the middle between a solid mass movement and a flow mass movement. I just put the input, and then it's very important using this input to perform a right choice in terms of mitigation of risk.
Yeah, thanks, Maria. I think, yeah, your area, whatever you have contributed through your research, is going to play the foundation, going to be the foundation stone of coming up with some engineering solution that can be implemented in the field.
Yeah.
And I think that can also be very much used or employed in designing of softwares that can also take into consideration your constitutive model and other parameters, and that can be validated with it. So it's a wonderful idea. I think, yeah, this kind of slide or a flow or you call it a debris flow is very much prominent in Italy, your area, right?
Yeah, not only in my area, both in certain and northern Italy, Campania and Liguria, and so also, but I found also in Norwegian area some example. For example, my colleague from Oslo sent me last year one event that occurs in June 2020. That is that was a landslide, flow side landslide. And also there are LARS in Chile or in other countries. This kind of landslide are common, especially in volcanic area, but can be also originated in other environmental contexts.
Right. I think we have lots of common area of research where both countries need a good collaboration. And because our landslide that we face in India is a little bit different in nature. And what you face is definitely, you're not countering much what we face here. So we can collaborate together to come up with some sort of what you can say that landslide inventory, where we come up with try to document all different type of landslides and their peculiar features that have taken place throughout the globe. I think definitely I will try to remain connected with you and will work over here soon. And so we have just 10 minutes left for our next lecture. And now I hope that it's afternoon there in Italy also.
Almost after.
Almost, right.
Yeah, 10 minutes for afternoon.
10 minutes for afternoon, right. So thank you very much. Thank you very much, Dr. Maria, to take out time from your Monday morning schedule. And
it's a very, very, very delightful opportunity for me.
Yeah. And I expect that you will be attending our lectures on landslides.
Yeah.
So one of the speaker previously to you were also a speaker on landslides. And I think tomorrow also we are having 2 speakers who will be speaking over landslides.
Yeah.
So that you can get an overview or idea what kind of landslides we face in India and what kind of problems you have in Italy. So that, we can come up with that landslide inventory sort of stuff.
Yeah, I want to join you for the whole conference.
Yeah, but I also understand that, you have your own research going on. So, but my request to you will be that if you get time, then take out some time for these topics, and then we can definitely collaborate, and can also put a few people from US, and can try to come up with something constructive and efficient work in this area. So thank you once again, Dr. Maria.
Thank you.
Thank you very much. Thank you. Have a good day. Bye-bye.
Yeah, you too.
Yeah. So dear participants, this was Dr. Maria from Italy. And now our next speaker would be Professor Priyanka Ghosh from IIT Kanpur. He will be joining us soon. He has joined? Okay, wonderful. So I think he has already joined. So we have 3-4 minutes before we start our next session. So for any query or suggestions, you can always put that in the WhatsApp group also, and also in the chat box. So it would be great that, through your suggestions or comments, we will try to make it a better workshop. Okay, so there were some questions regarding attendance and feedback. By the end of the next session, both things will be sent to you through a Google form. Okay? Yeah. So there will be a Google form where you need to fill up it for feedback. And I hope that you know the minimum criteria of AICTE to get the e-certificate for this workshop. That is, you must score 60% in your quiz that will be taking place in the last day of this workshop, and 80%, that is the criteria for attendance. So these are the two criteria where only those people who are fulfilling these two will be given the e-certificate by AICTE. So please keep that in mind. That's my request to all the participants. Yeah, I think we also have one question, that is email or on WhatsApp, share the feedback relentlessly. Yeah, I think we will be sending it here on the chat box also to keep it a little bit transparent. Okay, because in WhatsApp, what happens, everyone tries to, fill up that form. So we'll try to keep it in the chat box here. And I think within some time, I will be sharing the link here only. Yeah. Thank you, Mr. Ravinderji. Professor Ghosh, can you hear me?
Yeah, I am hearing. Yeah.
Yeah, very good afternoon to you, sir.
Yeah, good afternoon.
I think, sir, we'll be starting your lecture by 3:30.
No problem. I just wanted to check my connectivity and all. So that's why I entered a little bit early. So anyway, I'll be there after 3:30. Okay.
Yes, sir. Sure, sir. Thank you very much.
Okay.
I think, sir, we can start the session.
Yeah, no problem. Yeah.
I think your audio and video is okay, right, sir?
Yeah, I think so. Yeah.
Okay. So, good afternoon again to everyone. We have with us the last speaker of the day, Professor Priyanka Ghosh. He is a professor in the Department of Civil Engineering at IIT Kanpur. He has done his PhD from IIC Bangalore. And after that, he served as faculty at BITS Pilani, IIT Kharagpur, and then Kanpur. Sir's CV is very long, but I requested him to send me a brief resume. So I will try to take it a little bit more briefly. So Professor Ghosh is recipient of many prestigious awards, which includes Young Engineering Award given by Institute of Engineers India, Outstanding Young Investigator Award given by ICMAG USA, and after that he has also received scholarship for young Indian researchers by Italian Ministry of Education, University and Research, Indo-US Research Fellowship by Indo-US and SMP Forum. And Dr. Ghosh is currently also the editorial board of Indian Geotechnical Journal and International Journal of Geotechnical Engineering. He is serving as a PAC member at SERB, DST India, Associate Dean, Physical Infrastructure at IIT Kanpur, and Academic Program Director, IIT Kanpur, La Trobe University Research Academy. So Professor Ghosh, I heartily welcome you to this workshop. And thank you very much, sir, for giving us opportunity to make you part of this workshop. So thank you for accepting our invitation to deliver a lecture in this workshop. And sir will be speaking today on the topic active vibration screening in soil using geofoam and bamboos. Over to Priyanka Ghosh, sir.
Yeah. So am I audible?
Yes, sir, you are perfectly audible.
Okay, can I share my slide?
Yes, sir, sure, sir.
Okay, is it visible now?
Yes, sir, it's perfectly visible.
Okay. So thank you very much, Dr. Sharma, for the invitation. And I'm really honored for that. And good afternoon, ladies and gentlemen, and the participants. So today, actually, as Dr. Sharma pointed out, the topic is active vibration screening in soil using geofoam and bamboos. Now, before going to the actual presentation, so let me give you some background. So the topic or the title of the FTP is Disaster Resilient Infrastructure, right? So most of the times, maybe you will be coming across the hazards or the disaster induced by the earthquake, and which is quite obvious in India. Earthquake, tsunami, and then your landslide, rainfall, flood. These are the disaster generally happens in our country, and most of the times catastrophic failure happens due to that. Now, sometimes what happens, we neglect this part, but sometimes what happens, and this is more predominant in the present era, when you have scarcity of land, okay, and you have high population. So you don't have any other choice but to construct some structure, residential structure, nearby some industrial structure. Earlier, it was not like that, but now you are compelled to do that. Okay? So therefore, whether you call this is as disaster or disturbance or annoyance, but somehow this will create some discomfort to the inhabitants. That's for true. Okay. So therefore, we need to really think about that how to get rid of this kind of unwanted kind of situation. Now here in this presentation, I will be mainly talking about the vibration which is caused by the machines. Like you can have the vibration which is coming out from the factory, workshop, or any kind of industrial structure. Okay, and therefore the vibration which will be induced, that will be a little bit different than the vibration which is caused by the earthquake. Okay, so there are few things which are completely different than the earthquake vibration. Okay. Okay, so now there are two materials I'll be talking about. One is geofoam, which is a family member of your geosynthetic family. Okay, and another one is bamboo, which is natural.
I think there is some sort of connectivity issue. Professor Ghosh will be definitely joining us back. Because of some connectivity issue, he might have got disconnected. Apologies for that. He's back. Yeah, he will be joining.
Sorry, I was disconnected.
No issues, sir. We totally understand, and this kind of problem is always there online. Yeah. Sorry for no issues with that. You please carry on. Thank you.
Okay, is it visible now? Hello, am I audible?
Yes, sir, you are perfectly audible. Please carry on.
Okay.
Yes.
So, as I was mentioning about, so we'll be looking at applicability or the application potential of two different materials. One is geofoam, another one is bamboo. So geofoam is basically the artificial material or the synthetic material, but this is a family member of your geosynthetic. Whereas bamboo, it is a natural material and cheaply available in our country. So this will give you not only kind of disaster resilient infrastructure, at the same time you'll be using some kind of natural member, natural fiber to arrest or to screen the vibration, which is caused by some machines. So let's see. So there are, because, and now you may ask me why I have chosen these two materials. I'll be coming to that point very soon. So before going to the actual presentation, so this is my research profile. So I mainly work in the theoretical and experimental geomechanics. So these are the different. So these are the different topics or the maybe the field I work. So today I'll be talking about this part, that is vibration screening. Now, why this topic? Why is it required? Okay. So as I was telling, so this is the real motivation to carry out this work. So machines are one of the major sources of ground vibration, which may cause undesirable vibrations to the nearby structures and unpleasant condition to the inhabitants. Because, I mean, if you think of 30-40 years back, it was not the situation. At that time, you had plenty of land and population was also less. So you had the opportunity to choose or to select your structure or to select your land where you will be constructing your building or your house or whatever. But nowadays, you are compelled to do that, right? You are not having the luxury to choose your site which is away from any kind of undesirable or the unpleasant situation. Now, I can tell you, if you recall, there is one advertisement coming in the television, right, where the father is asking the son whether you will be able to construct your house near the railway track, right? So that is now. I mean, whatever I am telling, so this is coming to the reality. Okay, so you cannot get away from this. And the son was confused. So ultimately, there was some solution given by the company, and ultimately the advertisement comes out to the strong cement kind of thing. So this is not the question of strong cement. So I'll be coming to that point right now. Okay, so what I mean to say that you don't have any choice to select your land. Okay, you have the house. Immediately outside the house, you will be seeing the highway is moving, or the national highway, or the your railway track is moving, or maybe nearby some factories are coming up, some industry is coming up. So you have to deal with that. So therefore, to mitigate these ground vibration problems, out of different techniques, the installation of trench between the source and the receiver is found to be quite effective. Now, installation of trench. What is trench? Trench is nothing but you are taking out the soil, or you are excavating the soil out from the location. Now, as you know from the wave propagation theory, and I am quite sure that when you are talking about the disaster resilient infrastructure, when you have come to attend this FDP, so you know that elastic waves can only propagate through the elastic medium. So if you cut down the medium, so waves cannot propagate. So the idea comes from that. So you will be installing the trench. That means you will be taking out the soil material or the geotechnical material, so that it will be creating a void space, and through the void space wave cannot transmit. That means you are arresting or you are screening the waves. Okay. The present study is motivated towards the numerical investigation of screening efficiency of open trench, continuous and intermittent geofoam infill trench, and continuous and intermittent bamboo infill trench. So these three terms, open trench is pretty clear to you. That means you have the trench, okay, which is constructed or which is excavated. That is called open trench. Now, either you go for open trench or infill trench. That means you will be putting something inside the open trench, and that is called infill trench. Now, this infill trench could be continuously filled or intermittently filled. Depending on that, I have named two different orientation or two different configuration, rather, continuous geofoam infilled or intermittent geofoam infill. Similarly, by using bamboo, you have continuous or intermittent. So I'll be coming to those configurations when I'll be talking about those things in more detail. The idea of IF, that is intermittent geofoam or bamboo infill trench, has been newly implemented in the present investigation. So I'll be giving the idea. So this idea completely was conceptualized and was worked in our lab, and then it was proposed. Okay. Now, here I'll be restricting myself only on the numerical analysis of the problem. However, experimental things I will not be discussing here. So, finite element method has been adopted for this numerical investigation. Now, let's see. Now, before going to the detailed discussion, what are the different types of machines we need to identify? First one is low to medium frequency machines. Frequency generally varies from 0 to 10 Hertz. For example, large reciprocating engines, compressors, and blowers. Now, second category is medium to high frequency machines. Frequency ranges from 5 to 17 Hertz. For example, diesel and gas engines. So the third category is very high frequency machines. Frequency is more than 17 Hertz, like turbo generators and combustion engines. Now, these machines can operate causing unacceptable displacement, annoyance, shaking, heat, etc. So these are the things you don't plan for when actually you are going to install some machines. You don't plan for any kind of unacceptable displacement or annoyance or shaking or heat generation, right? So we'll not be talking about anything regarding this heat generation. However, we'll be talking about unacceptable displacement, annoyance, and shaking. So we'll be concentrating more on these aspects, okay? And these things are coming, I mean, there are several reasons for which these things may come. So we'll come to that point right now. Now, repeating forces. Now, what are the different sources of machine vibrations, or I mean this kind of unwanted situation, okay, when it happens. The repeating force is due to the rotation of unbalanced, misaligned, worn, or improperly driven machine components. Now, if you look at different pictures shown here, like here, so this is, I mean, you have the uneven rotor, which will cause unwanted vibration. Similarly, bend shaft. I mean, these are the things. I mean, you may tell me, or you may ask me that why should I consider these things? Because these are the defects, right? These are the outcome of poor maintenance. Yes, I agree. I do agree with you. These are the things which will be coming due to poor maintenance. Now, if suppose due to this poor maintenance, if this happens, then who will be suffering? You will be suffering, where actually your house is, right? So therefore, you have to think, or these are the things basically should come from the engineer or the scientist, that you need to foresee the problem. It is not like that you cannot say that this is not my problem, this is the problem caused by someone else. Why should I suffer? You cannot say. At least in our country, this doesn't work, right? You cannot, I mean, you can blame, but nothing will happen. You have to take care of your own things. So this is the thing. That's what I'm saying. So if there is bent shaft, now who will be suffering? You will be suffering. And that is because of poor maintenance from the owner. But that owner may or may not take care of that. But ultimately you have to realize, or you have to take care of your house. Okay. Now sometimes parallel misalignment, due to that you can have unwanted vibration, or excessive clearance. So this is the clearance which becomes excessive or unacceptable, okay, due to continuous movement of the machine, and due to that you have unwanted vibration. Now these are the causes. Apart from these causes, there are several other causes for which you will be getting the vibration coming from the machine. I mean, extra or additional vibration or unwanted vibration. So, but your job, at least in this particular study, our job is to protect our structure from this kind of unwanted vibration. We anticipate that machines will give some unwanted vibration, will cause some unwanted vibration, and we are going to arrest it. That's all. Just a minute. I think my PPT has been stopped.
It's okay, sir. No issues.
Yeah. Is it coming now?
Yes, sir. Yes, it is there.
Okay. Now, what are the different mitigation techniques of ground vibrations? As you know, from the geotechnical earthquake engineering field, you know that there are several mitigation techniques for ground vibrations. One is base isolator, like, I mean, as you can see from this place, I mean, these figures, right? These are huge base isolators. Okay. Now, machine-induced vibration can be reduced by using damping devices or base isolator, as I was telling, at the foundation base, but sometimes it is not possible technically or economically. Now, first of all, I am coming to the technical point of view. So why is it not possible technically? Suppose you have the existing structure, which are, or maybe you are, at least in India, you have several heritage structure. I mean, for when I am talking about the heritage structure, one incident is coming to my mind. So a few years back, actually, I was approached to work on some problem in Agra. There was some heritage structure which was constructed long back, I mean, during Mughal Empire. At the time, that structure was constructed, and now some railway track is going side by, okay, nearby. And due to that railway track, I mean, heavy goods vehicles are moving, and due to that, some vibrations are coming to the heritage structure, and heritage structure is in danger. Okay, so that kind of problem was actually was sent to me. So that was the genesis of thinking. Okay, so let's talk about, or let's think about some practical solution. Okay, which will be cost effective and at the same time which will be really achievable. Because in our country, if we propose something very costly thing, people may or may not achieve it. Okay, so therefore that was the motivation. Anyway, so now technically you may or may not be able to put some base isolator or the damping devices at the bottom of the structure, existing structure. Okay, but you need to arrest the vibration which is coming from nearby, say some kind of source, or sometimes it is not economical. Suppose if you go for some 2-storied or 3-storied small house or the apartment, and if you put this kind of huge base isolators, okay, at least in India, in our country, it will not be economically effective. Okay, so therefore we need to think about some alternative solution so that we'll be getting some effective vibration isolation, but at some minimum cost. So what is the practical solution, or what is the feasible solution, cost-effective solution? Installation of trench or barriers across the path of propagating waves would be an effective solution for vibration screening. Now you can see, so let me switch on the pointer. Okay, here you can see this is the open trench as I was mentioning. Okay, so you are excavating the trench. That means you are taking out the material inside from inside the trench, right? So therefore what will happen? The elastic waves cannot propagate. Suppose if the source is on this side, the transmitting waves cannot propagate across the trench. That is the idea. Very cheap, cost effective, or sometimes you can put some material inside the trench, and this is called infill trench as I was mentioning. Okay, so as you can see, some material which is having the potential of vibration screening, so those materials are put inside the trench to give you vibration isolation. Now overview of vibration screening system. So as you may be knowing that there are 2 different types of vibration isolation. One is active isolation, another one is passive isolation. So in this situation also, so I am not going to use this word isolation because there is a fine difference between the word isolation and screening. Okay, I am very much comfortable with the word screening, at least for this study is concerned. Okay, we are screening the vibration. We are not isolating the structure from the vibration. Okay. So anyway, so now in case of active screening, say using some circular open trench, what we do here basically we try to cut off, okay, or we try to eliminate the source which is causing the vibration. So you can see this is the foundation. On top of that you have some oscillating force which is causing some vibration. So this is your dynamic amplitude or acceleration or displacement, whatever you say, amplitude of surface displacement you say, and you are excavating circular open trench, annular trench, okay, all round. So this is the all round annular trench, so that this source is completely cut off from the rest of the part. So now you can see, so this is some kind of schematic diagram. So now you can see the amplitude just near the source was this much. Okay, now it has been reduced to this much. That means you are screening. So you cannot stop completely. Little bit of vibration will be going on the other side because you are not going for continuous trench, and it is not feasible also, right? You have to stop somewhere else. So therefore some waves will be anyway passing below the trench. So therefore you will be getting some amplitude of surface displacement, but that will be very nominal. Okay. Similarly, you have passive screening. So in case of passive screening, where the source is far away, okay, and you are trying to protect your structure. So this is some sensitive building or the structure which you want to protect from the vibration. So therefore, you are excavating the trench near to the structure, okay, proposed structure. So therefore, whatever vibrations or whatever waves are coming coming out from the source, that will be arrested in this trench. Okay, so this is called passive. That means you are not directly eliminating the source, rather you are protecting the structure. So we'll be talking about this active screening system in this particular talk. We'll not be talking about this passive isolation or the screening, which is pretty predominant in case of geotechnical earthquake. Okay, but in case of machine-induced vibration, we generally eliminate or cut off the source itself. Okay, so in this particular talk, we'll be restricting ourselves, or we'll be talking only about the active screening system. Now, these are the literature related to open trench. It started in 1962, long back, by Burkan, 1962. So he started with open trench with sheet pile wall. But I mean, he did some field investigation, but he was unsuccessful to get screening of traffic-induced vibration, because he tried with that, but he didn't get the success. Later in 1968, Woods used open trench and sheet pile wall for both active and passive screening in field investigation, and he showed he came to the conclusion that he came to the conclusion that about the geometric parameters of the trench. So he basically optimized different trench parameters, trench geometry. Okay, that means width of the trench, depth of the trench, length of the trench. So these are the things he tried to optimize. Now later in 1978, Segal et al. Used open and infill trench in numerical investigation. So barriers are effective in reducing vertical displacement. So that was the conclusion came out from this study. Later, Bescos et al. In 1985 used boundary element method, BEM. Okay, and they tried with open trenches. I mean, they came out with the conclusion that the open trenches are more effective than infill trench. Okay, infill trench means what? You are extracting the parent material, but you are putting some foreign material. But it depends. The screening is now basically it is not 100% void space, right? You are putting some foreign material. Now this effectiveness of your vibration isolation or the screening completely depends on the material behavior of the foreign material, isn't it? So therefore, of course, the infill trench will not be giving you as good screening as possible in case of open trench. Now, one thing is very clear from this study, that open trench tops the list. Okay, so it is the best vibration screening system. But there are several difficulties involved with the open trench. What are those? Now, open trench faces several technical problems, such as you may get unnecessary bulging on the sidewall, you may get sand pockets or sloughing, you may get localized collapse, or sometimes if you have this kind of strata, strong layer over weak layer, or weak layer over strong layer, you may get this kind of failure in the weak layer, right? So ultimately your open trench will collapse. So if the open trench gets collapsed, then your whole idea has gone. Your objective was to create some kind of void space. Now if the open trench gets collapsed, then what will give you the void space? Nothing. So ultimately it will be filled with some soil. So open trench suffers a lot from the stability issue. So therefore people have gone for infill trench, so that you will put something inside the open trench which will try to protect the failure of the open trench. That was the idea, or that was the motivation for the researchers to go for infill trench. Now, what are the literature? These are the main, say, works or the major works on infill trench. In 1981, Hoft used solid concrete walls, lightweight barriers such as row of boreholes, and he used model test on artificially dense sand. Then later in 1996, Al-Husseini and Ahmad used concrete and soil bentonite filled trench, and they used BEM, that is boundary element method, with active screening technique. In 1999, Cortez et al. Used rows of piles, conventional piles, and advanced frequency domain boundary element method was used by them. Later, Massars in 2005 used gas cushion with self-hardening cement concrete, cement bentonite, and he went for full-scale application. Okay, so these are the major studies on infill trenches using different materials. As you can see, solid concrete walls, soil bentonite field trench, rows of pile, gas cushion, and all the and several others, right? Okay, now coming to our problem. So what actually we are supposed to discuss today. So geoform infill trench. So now geoform, EPS geoform, expanded polystyrene geoform. Okay, so that is used by several researchers in different activities. Okay, for the different purposes. Now, Davis 1994 used EPS geoform as vibration screening material due to its low acoustic impedance. So this is very important word, this acoustic impedance. It should be the difference between the parent material and the infill material, difference of acoustic impedance should be very high. There only you'll be getting better screening efficiency. Okay, so due to its low acoustic impedance, it is very effective in reducing blast-induced vibration. Okay. Then Horvath, 1994, used EPS geoform as compressible inclusive material in retaining wall under static as well as dynamic loading. So he used EPS geoform between the soil backfill and the retaining wall, and then because of this high compressible nature of the geoform, he used to achieve the low lateral pressure. It could be active or passive on the retaining wall. Okay, so that was the study. But for that purpose, actually, he used geoform. Now, Wang et al. 2008, efficiency of EPS field trench has been compared with open trench, inundated water trench with different configurations. Now, Alzoy and Elnagar 2011 used numerical and experimental investigation with different configuration of EPS field trench. Now, in this particular study, what is our approach? The approach is, first one is the investigation of screening effectiveness of OT, that is open trench, CF, that is continuous infill trench, as well as IF, that is intermediate infill trench, whereas the concept of IF has not been implemented by any researcher earlier. Determination of optimized values of geometric parameters for different trench conditions. Okay, so we'll be optimizing the geometric parameters, like as I was telling, that the trench geometry. So that needs to be optimized. Otherwise, you cannot go for infinite length of trench, infinite depth of trench. It is not possible, not feasible, right? You have to stop somewhere. Now, where to stop? That will be coming from the study. A simplified design methodology is tried to derive such that this trench condition can be implemented in the field easily. Okay. Now, two different foundations have been considered. One is strip, that is two-dimensional or the plane strain condition, and circular foundation excited by dynamic loading. So, strip was considered to get some kind of plane strain kind of situation, and circular was used to get some kind of axisymmetric kind of situation. However, in case of strip, we considered the trench on one side of the foundation, whereas in case of circular, we considered the annular trench, as I was showing earlier when I was talking about the active screening system. So you have all-round trench. Okay. Now coming to the problem definition. So two different problems. So right now I am talking about the geofoam infill trench. Okay. So later on I'll be talking about the bamboo infill trench. Okay. So geofoam infill trench. So the active screening using trench for strip foundation. So this is your foundation, strip foundation. The depth of foundation. So this is the embedded foundation, of course. This is the width of foundation. Now this is a trench, okay, which is placed on one side of the foundation. So small d is your depth of trench, small w is your width of trench, and length of trench is immaterial because you are dealing with plane strain problem. Now this is the whole soil domain, okay, which has been optimized based on some sensitivity analysis. I'll be talking about that thing later on. Now, what we did, we applied some dynamic load on top of the foundation, and we selected some pickup points where we actually captured the amplitude, okay, displacement amplitude, so that we can calculate or we can determine that how much reduction is happening due to the presence of this trench. Okay, so this is the idea. Similarly, in case of problem 2, where we dealt with circular foundation, so there you have the foundation here, and you have all-round trench. Okay, so this is a kind of annular kind of arrangement, and this problem is completely symmetric, right? Axisymmetric problem. You can see that from here. Whether you consider pickup points on this side or this side doesn't matter. But in this problem, problem 1, the pickup points should be on this side, because then only you will be getting the effectiveness of the trench. On this side, if you put the pickup points, then there is no point of putting the pickup points there, because that is, these pickup points will be capturing the normal or the natural phenomenon. Okay. Now coming to the EPS geofoam, you may ask me, or you may, I mean, this doubt may come to your mind that why I have chosen geofoam. There are several other materials in geosynthetic family, right? Why I have chosen geofoam? So there is some specialty of geofoam. Okay, the structure wise, it has got some kind of potential to be used for screening system. Now, EPS geofoam has tri-dimensional closed cell arrangement. 95% of volume is occupied by air. Now, what we need in field trench, what we need, what property should be there for the infill material? It should have maximum void space, okay, so that waves cannot transmit properly. And the geofoam has got that. 95% of volume is occupied by air. So it has got some kind of potential to be used for active screening or screening system. Now, EPS geofoam behaves as linearly elastic. It is highly compressible and very elastic material. So linearly elastic material up to 1% of strain. Can you imagine? Up to 1% of strain, it will behave as linear elastic. And up to 5% of strain, it will behave as non-linear elastic, and thereon it will be going for plasticity. So generally, in case of machine foundation, if you really recall about the machine foundation design, you generally consider the elastic bed or the elastic half space, right? So no way you expect your strain level will go to the plasticity. Okay, so therefore it is very good from the strain point of view as well. Now these are the properties of EPS GeoFi as per ASTM D6817. So these are the different densities available in the market. Okay, and you can see the density is 1% of the traditional art material. So density wise, it is very, very low. Elastic modulus, Poisson ratio, shear wave velocity, everything is given. Now this is the acoustic impedance. Okay, so this is the formula for acoustic impedance. So you can calculate acoustic impedance, which is coming as 7.72 kilonewton second per meter cube. Okay, now you see here, the lower acoustic impedance will transmit smaller amplitude of waves. Okay, so your idea should be always to choose that material which will be giving you very low value of acoustic impedance. Okay. Now coming to the constitutive model for different materials, what we chose for this study. Concrete footing has been modeled as rigid non-porous material, assuming RCC material. Now I am coming more towards the numerical modeling aspects. The properties are assumed as per this paper or this study. Air voids or pockets in the IF, intermittent geoform infill range. So now what are these air voids or pockets? I'll come to that point, okay, immediately after this. So it is filled with air. Okay, so it is the completely void space. That's all. Okay, so that is considered as very low stiffness material, and Poisson ratio is equal to 0, and E reference is very, very low. You can see from here. Okay, that is the elastic modulus. Now soil is considered as linear elastic because, as I told you just now, we are not expecting any kind of plastic deformation in the machine foundation. Okay, so therefore the elastic model in soil is fair enough. Okay, and the geoform is also considered as linear elastic. And now in the numerical modeling, 5% material damping is considered as per Rayleigh damping. 6 noted triangular elements are chosen for domain discretization. So these are the numerical or the finite element model details. So I am not going to those details much here because that will not give you much interest at this moment. At flexible joints between soil and footing, interface elements are provided. Now this is the soil medium, okay, which is considered in the study. So total depth of the soil deposit was considered as 11.7. So where the first 3 meter, top 3 meter depth is deposit 1, then deposit 2, deposit 3, deposit 4, and deposit 5 is considered when all the, see, we considered 5 cases. First case is that first 4 cases are homogeneous soil deposit, where the whole stratum or whole profile is filled or is made of the deposit 1 or deposit 2 or deposit 3 or deposit 4. So these 4 cases gave me the homogeneous soil profile. But we also wanted to capture or also wanted to see the behavior in the non-homogeneous layered deposit. So in that situation, deposit 5 is considered, where all 4 deposits are lying like this: 3 meter, 3 meter, 3 meter, and 2.7 meter. And this has been taken from this study. Now these are the dynamic properties of soil deposits. Okay, various properties were worked out: static modulus, dynamic modulus, shear wave velocity, primary wave velocity, and so on. Now coming to the boundary conditions. So absorbent boundaries are provided as per Lismer-Kulemer 1969 recommendation. So viscous absorbent boundaries are proposed all around. Okay, this is the schematic diagram shown here. Now in case of static and dynamic loading, so what we put here, this is the harmonic load, vertical harmonic loading of amplitude 1 kilonewton was applied on top of the foundation. In addition to that, static load intensity of 10 kPa is applied as the weight of, so static weight of machines and other components. To consider that thing, we put 10 kPa static load on top of the foundation. Now, this is the domain size sensitivity, as I was mentioning earlier, that how we have got the domain size. That means the width of the whole domain, soil domain. Depth of the domain is fixed, that is 11.7 meter. But the how we have got the width of the domain. So that came from this sensitivity analysis, as you can see. So this is the average displacement along the boundary. And for problem 1 and problem 2, you can see that when the element size is beyond, say, 3 lambda, lambda is the wavelength for radio wave, okay? So beyond 3 lambda, basically it is almost constant. So we can choose like 3 lambda for the analysis. Now, if we choose very, say domain size is very big, okay? So this is 3 lambda is your domain size, okay? So if we choose, suppose 4 lambda or 4.5 lambda, we can choose. But what will happen? You have your computational time will be increased unnecessarily. So to optimize that computational time as well as to get the proper solution, we did this sensitivity analysis. From there, we chose the domain size. Now, next job is to choose the element size. Now, this is the average element size. So this is lambda r by 8 criteria. It should be like that. I mean, this is the criteria fixed by different researchers. So average element size is 0.121 lambda r. Based on this, finer meshes are chosen. So this is average element size. Please try to understand. And we have considered some graded meshes. Therefore, near the foundation or near the footing, the element size is pretty small, whereas at near the boundary, the element size is a little bit bigger. However, the average element size was 0.121 lambda. And that is inconsistent with the recommendation of the element size, because element size cannot be very big so that the waves cannot transmit. So, okay, these are the numerical issues you need to think during the finite element analysis. Okay, now concept of intermittent geoform, as I was mentioning. Now, what is intermittent geoform? Why is it called intermittent geoform? So this is the trench, okay? So here what we did, we put one block of geoform and then we put this space as open space or the void space or the air void, okay? And these are called pockets. Then again, second block of geoform we put, and then again air voids and so on. So basically this is the alternative arrangement of geoform block and the air voids. And that's why it is called intermittent geoform. What is your target? Your target is to reach up to the open trench condition. But if you go to the open trench, you have seen that open trench suffers from different issues, different instability problems. So therefore, in this kind of arrangement, these blocks, geoform blocks, will try to stabilize the wall of the open trench. And these, anyway, geoform will, I mean, these geoform blocks themselves have the potential of screening system. At the same time, these air pockets or the air voids, these will act as open trench. So you will be getting better efficiency of the trench. Okay, instead of putting, and at the same time, you are saving the material as well, because geoform is not cheaply available. Okay, this is manufactured material, manufactured by different companies, like geosynthetic companies. So therefore, it is not easily available or cheaply available. Okay, so that's why we considered. So there are two aspects are achieved here. You are getting better efficiency, screening efficiency, and at the same time, cost is less because you are consuming less material. Now here, actually, now you may ask me that on what basis we have chosen this depth of air pockets. Okay, so that was calculated based on unsupported length criteria. That means up to this date, the soil will not collapse due to its own weight or the self weight. Okay, so as you know, that is pretty much available in the conventional soil mechanics book, that is unsupported length. So based on that, satisfying that criteria, we chose the size of the pocket, air pocket. Now this is for the second problem, that is circular foundation problem. You have all-round trench, so alternate arrangement of geofoam and air pockets. So this is the geometry of the intermittent geofoam. You can see this is the long, say, geofoam block, then air pocket, then alternately another next layer of geofoam, then air pocket, and so on. So these are the dimensions, or these are the geometry considered for the air pocket, intermittent infield trench. Now this is a nomenclature which is used for this study. ARF, that is very, very important parameter, that is amplitude reduction factor, which is defined as the ratio of peak vertical displacement with and without trench. And this is proposed, this definition is proposed by Woods in 1968, and we didn't change anywhere because there was no requirement for changing this. We followed the same definition of ARF. So what is this? UV after means that is the peak vertical displacement with trench, okay? And this is the peak vertical displacement without trench. So that means from this expression, it is very clear to you that any arrangement which is giving you lower ARF, that is better or the efficient screening system. Agreed? That means your target should be always to achieve lower ARF for any system. It could be open trench, it could be continuous field trench, or it could be intermittent field trench. Your idea or your target should be always to get as low as possible ARF. Now this is the nomenclature we used: Li, Wj, Dk, Fm, In, and this part. So I'll just explain each and every parameter, the meaning of each and every parameter, so that when I'll be showing the graphs, at that time you'll be able to follow it. Okay, so L is location factor. What is location factor? Location means the distance between the source and the trench, normalized with respect to the wavelength of Rayleigh wave. That means L, if the small l is the distance between the source and the trench, then small l by lambda r is your capital L. Is it clear? Similarly, W, which is width factor, this is nothing but the width of the trench normalized with respect to lambda r. Capital D, that is depth factor, that means the depth of trench normalized with respect to lambda r. Similarly, F is frequency of excitation. Okay, so that is not normalized at all. I is another parameter, inclination of trench. Now, as long as whatever figure I have shown, there every time you have seen the trench is vertical, right? Now, trench can be also installed in the inclined direction. Okay, depending on the inclination, you will be getting the better better screening efficiency. I'll come to that point. Now, if the trench is vertical, at that time your inclination of trench is 90 degrees. Okay, I is 90. If the trench is moving towards the source, I'll show that thing later on, by 45 degrees, then I will be 45 degrees, something like that. Okay. Now, LE is linear elastic material. I mean, when the soil is considered linear elastic, of course, we did analyze nonlinear, considering soil as nonlinear elastic. However, that thing I am not showing here. Okay, so that will be taking too much of time. So that's why I am excluding. So therefore, now you can see, so Li means I value will be this I, this subscript will give you the value of that L, that location factor. W is the width factor, D is the depth factor, F is the frequency, I is the inclination, LE or NL, depending on that, you will be getting linear elastic or non-linear elastic. In this particular presentation, we'll be concentrating only on linear elastic. And IF stands for intermittent geoform, OT stands for open trench, CF stands for continuous form. Okay. Now coming to the results. Now here, this is the vertical displacement versus time for nearest pickup points for problem 1 in deposit 1. Okay, deposit 1 means homogeneous deposit made of deposit 1 as I was showing earlier. Now you can see, so this is the vertical displacement along y-axis and this is the time, okay, along x-axis. Now you see, this is without trench, that means normal ground. Okay, there is no trench installed in the ground. At that time, these are the peaks or the the displacements you are getting. Now after putting, now you see this red one stands for CF, continuous form, blue one stands for IF, and green one stands for OT. Now you see, first we'll come to CF. Now you see, when CF is installed, at that time the vertical amplitude or the vertical displacement amplitude reduces drastically. That means this much, this was the peak displacement in case of without trench condition. Immediately you put CF, it comes down to here. Okay. Now you come to OT, that is open trench. That is the ideal one. So this green one is the open trench. You see the peak vertical displacement amplitude reduces significantly compared to the without trench condition. So now you see the screening efficiency. Okay, so open trench gives you the maximum screening efficiency. However, this infill trench, the blue one, now you see this is pretty close to open trench. You cannot achieve, the open trench is the benchmark kind of thing. That is the lowest possible situation. You cannot achieve open trench condition by infill trench, but you can reach up to the open trench, or you can proceed, or you can tend towards the open trench condition by reducing the material in CF and by introducing the concept of IF. That is the thing I was emphasizing since beginning. I hope that you have understood the concept of IF and the advantage of IF. Okay. Now this is for problem 1 again. This is for farthest pickup point. So that was this one is nearest pickup point. Okay, nearest pickup point vertical displacement of course will be higher because due to damping it will be decaying at the farthest pickup point, and now you can see here also scenario is same. That is the without trench is giving you the maximum and the open trench is giving you the minimum. And IF is very close to open trench, but you cannot achieve the situation of open trench but IF again. Anyway, now coming to the effect of location of trench. So where to locate your trench? Now these are the things will be coming to your mind. Now where should I place the trench? How much depth should I go? What should be the width of the trench? So these are the questions will be coming immediately in your mind. Okay. Now effect of location of trench. Now you see for problem 1 and problem 2 both qualitative or the trend wise both are same. Only thing is that the value wise it is different. Now you see here basically by keeping other things constant, okay, you see W, that is the width factor, we consider 0.06 for all, depth factor 1, frequency we consider 5, inclination we consider 90 degree, that means vertical trench we consider, and everywhere we consider IF. Okay, at that time we varied L, that is location factor from 0.3 to, or rather 0.1 to 0.3. Now L 0.3 means the distance between the source and the trench is maximum. L 0.1 is minimum. Now what is your intuition? That means if the trench is pretty close to the source, then you will be getting better efficiency, right? So immediately near to the source itself, you are cutting down the vibration. So that you are observing here. When L is 0.1, you are getting the lowest ARF distribution. Whereas when L is 0.3, you are getting the maximum ARF distribution. Similar thing you are observing for problem 2. That means when the foundation is circular. Now coming to the effect of width of trench. Okay. Now you see here what you are varying. You are varying the width of the trench, keeping L as 0.15 every case. Okay, D as 0.1, F as 5, I as 90. Only you varied W 0.08 to or rather 0.02 to 0.08. Okay. Now you see, if you increase the width of trench, what will happen? If you increase the width of trench, that means you are putting more foreign material. In this case, this is geofoam. That means if you put more geofoam in place of parent material, that is your soil. So therefore, you will be getting better efficiency. That means ARF goes down with increase in W. Okay, so your ARF goes down. And when the width is 0.02, that means you are using very nominal width of geofoam. At that time, your ARF is here. Now, in this case, this is your problem 1. But for problem 2, because you are in problem 2, what you are doing, you are getting all around trench. So you will be getting better efficiency in this situation. Now you see, so but the trend wise same. If W is 0.08, you are getting the lowest ARF. If W is 0.02, you are getting the maximum ARF distribution. Okay. So that means as your width of trench increases, you are getting better efficiency. Now coming to the depth of trench. Okay. So you are here, you can see other things we have kept fixed. Only thing is that we have varied D 0.8 to 1.2. So when D was 0.8, you are observing the ARF distribution is here. Whereas when D is 1.2, at that time ARF distribution comes down to this. So that means as you increase the depth of trench, you will be getting better screening efficiency. And that is true for problem 2 as well. Now here you see that the variation among the depth, okay, the variation of ARF among the depth is pretty significant. D 0.8 to 1, it comes down drastically. 0.1 to 1.2, it comes down. It was not the case for width or the location. So therefore, one conclusion you can draw from this, the depth of trench plays a very crucial role in vibration isolation for the screen. Now why? Now effectiveness of depth of trench. Now depth is found to be the most important geometric parameter. Okay. Now why? Now this is the depth of trench. Okay. This is the trench. Okay. So now the waves are moving like that. Now these whatever waves are coming in this zone, they will be restricted by this trench because the material will not allow, or it will allow very nominal amount of vibration. But what about the vibrations which are coming below the trench? They will be passing through. Nothing is there to restrict their movement. Now you increase the depth. Now you increase the depth. So more and more vibrations or more and more waves will be getting reflected back. So therefore you will be getting better efficiency. Is it clear? So ARF will be reduced further. Now coming to the frequency of source of excitation. So here you can see as your frequency increases, your ARF decreases. That means with the increase of frequency of the machine, you will be getting better screening efficiency. And this is very, very interesting observation. That means if you use high frequency machine, at the very first stage, I was discussing about different frequency range of machines, right? Low frequency, moderate frequency, and high frequency. Now, this kind of technology or this kind of phenomena is pretty effective for high frequency machines. Okay. Now coming to inclination of trench. Now you see This is the I-90. This is for I-90 when the trench is vertical. Now, if trench is inclined to 60 degree towards the source, it comes down to this ARF. And if it is 45 degree, it further reduces. Okay. Now, why? What is happening here? So this is coming from the wave reflection technology or the phenomena. See, this is your vertical trench. Okay, this is your vertical trench when I is 90 degree. Now this is your inclined trench when I is say 60 degree or 45 degree. Now you see, if this is the vertical, so these are the waves are coming up to this level, and then it is getting reduced, and then it is coming to this side. But if you are putting inclined trench, more and more waves will be resisted by this trench, and then they will be reflected back. So therefore, inclined trench is very, very effective. Now the question is that, okay, $100 question, that is how to install this inclined trench. Right now, I mean, how you will be installing this thing, this intermittent geoform or continuous geoform infill trench. Inclined trench is very, very difficult. Okay, so some technology has to be evolved. I don't have the technology right now for the inclined trench. Okay, so somebody may come out with the installation of the inclined trench technology. Anyway, now coming to the stiffness of soil, as I was telling, just a minute. Okay. So as I was mentioning about the stiffness of soil deposit, you can see that deposit 1 is the lowest stiffness soil in this particular study, whereas deposit 4 is the highest stiffness soil as far as the homogeneous deposit is concerned, whereas deposit 5 is non-homogeneous layered soil. And you can see as your stiffness increases, your efficiency increases. That means your ARF decreases. Okay. So that means in stiff soil you will be getting better, or where the stiffness is more, you will be getting better screening efficiency. Now coming to the geoform density, here it is just different. Okay, it is just reverse. If you use more soft geoform, you will be getting better efficiency. That you can see from here. So EPS 29 to EPS 12. EPS 12 is having the density 11.2 kg per meter cube, whereas EPS 29 is 28.8 kg per meter cube. You see that EPS 29, the ARF distribution is here, whereas for EPS 12, the ARF distribution is here. Okay, much lower. So if you want to really achieve better efficiency, you go for lower value of EPS, I mean EPS 12 or EPS 15, something like that. Now coming to the comparison. So this is a kind of validation, rather comparison. So this part is giving you the validation, this part is giving you the comparison. Now this is the validation of the present study with published work of Curtis et al. And Arzoy Elnagar for open trench. Okay, so nobody has used intermittent geoform. This was the first time we proposed that concept. So therefore, we are not able to compare with any other studies. But open trench people have worked, people have used. So therefore, we consider and we saw that fairly good match among the available studies. Okay, now coming to the comparison with the present study. Now you see, all parameters are remaining same. Only we are varying the trench configuration, CF, IF, and OT. Now, if you look at CF, okay, so this is the top one is CF, which is quite obvious, right? That will be giving you the lowest efficiency. That means ARF distribution will be the maximum. And OT is the benchmark. That is the lowest possible situation you can achieve. Now, you see IF, it is coming in between. So IF is always giving you better efficiency than CF, but of course, it will be higher than the OT response. Now, here I would like to tell you. Now, see, in IF, what was the configuration? You are putting the geofoam block and the air pocket in the alternative arrangement. Now, you can play with this. Now, you can increase the size of air pocket. Okay, of course, that unsupported vertical cut criteria must be satisfied. Now, you can play with the vertical or the air pocket, or you can play with the density of the geofoam in the geofoam block. Okay, by playing with the parameters, you can further reduce the ARF distribution and you can come close to OT situation. You cannot achieve OT situation because that is the lowest possible situation. So, but you can come very close to OT situation. Now, coming to the summary for this work, this geofoam infill trench work, depth of the trench is found to be the most important parameter. The screening efficiency increases significantly with increasing depth of the trench for all cases. D should be greater than 0.6 for getting effective screening efficiency in most of the cases. So this is the screening efficiency given for different depths and different trench conditions. Now, optimum design guidelines of IA is presented in the table below based on this study. Of course, based on the soil deposit considered in this study. So for problem 1, location factor is 0.15. For problem 2, it is remaining same 0.15. Width is also 0.06 for both the cases, and depth is 1 for both the cases. So, I mean, this is the optimum design guideline. So, I mean, with this, basically, you'll be observing maximum efficiency of air. Yeah. Now, coming to the source of excitation, it is found that for all the trench conditions, the screening efficiency increases with increase in the excitation frequency, which means this is effective in case of high frequency dynamic sources like turbo generators, internal combustion engines, etc. The trench inclination, coming to the trench inclination, that is the new kind of concept, at least for this study. For IF, in case of problem 1 with change in inclination angle from 90 degree to 45 degree, screening efficiency increases from 67.04% to 78.9%. Whereas for problem 2, screening efficiency changes from 64.54 to 78.77% for same change in inclination angle. Now coming to some field implementation issues, like now the question is coming, how to install this, right? So we have given some solution for that. Of course, tentative solution, it needs to be worked out more by applying that thing in the field. So how will install the intermittent geofoam? So first you take one, say, barrier, side barrier, so that can be made of some steel stiffener or the steel net or the fiber net stiffener and thin barrier, some PVC barrier. On top of that, you place the first EPS block, then you keep the air pocket, okay? Then you put the second block, and then you keep the air pocket in step 3. Then you put the third block, and then you put the top cover, okay, which is pretty similar to the bottom cover. And then the whole thing can be lifted and can be put in the trench, so that the trench will not collapse inside, because this side cover will try to protect that kind of bulging or the failure of the trench inside. And at the same time, these air pockets will serve the purpose of your intermittent geofoam infill trench. And if geofoam gets damaged, now that is the also question, right? You have to think about the sustainable solution. If geofoam gets damaged, then you take out the whole panel, you remove the top cover, you replace the geofoam blocks,
Professor Ghosh, are you connected? Still connected? I think we have again faced some sort of connection. He will be definitely soon getting connected back to us. So I think we can wait for a minute so that he can join us back. Before I think he joins us back, I think I have already shared a link in the chat box that needs to be filled up by all the participants for their feedback and attendance we are directly taking from these programs. So that's how we are presently doing it up. So I hope that, yes, sir.
Yeah, again got disconnected.
No issues, sir. No, you please carry on. I think you were in your last slide only, I think.
Okay. Okay.
Yeah. Please go ahead. Yeah.
So this slide was visible?
No. I think this was the one which was not visible. Please go ahead.
Okay.
Yeah.
This was visible, right?
Right. We were here. You were telling us about how to avoid that, whether that
installation process I was talking about.
Right.
Okay. So let me start from this. Okay.
Yeah.
So my time is up to 5:30, right?
Right. You have a lot of time.
Okay.
Thank you.
Okay. So coming to the bamboo infiltrate. Now, why I have chosen bamboo? Because as you know, there are a few points here. As you know, in our country, bamboo is easily available. Particularly northeast, you will be getting plenty of good quality bamboo. Now, second thing is that bamboo is having some inherent property, which is having the internal annular void space. Okay, and that void space, basically, your trench or the screening material should have some kind of void space. That means it should have that some kind of discontinuity in the material or the elastic material. Okay, so therefore you will be getting more and more screening. So bamboo is having this inherent quality. This is cheaply available and easily available and available in plenty. Okay, so therefore we thought, okay, let's go for some low cost vibration screening system using bamboo. So nobody has thought about yet. So, I mean, we proposed the numerical solution for this, and right now we are working on the experimental front. Now, what is the approach? The investigation of screening effectiveness of BIT, bamboo infill trench, whereas the concept of BIT has not been implemented by any researcher. Okay, so determination of optimized values of, and you know, this, when I am talking about this bamboo, later on I realized that the government of India has taken some initiative to work on this bamboo. Okay, some bamboo mission. So they are trying to use more and more bamboo in different fronts, from structural component in civil engineering, starting from that. So in that way, it is very much in line with the requirement of the country. So determination of optimized values of geometric parameters for different trench conditions. Simplified design methodology is tried to derive such that this trench condition can be implemented in the field easily. A square foundation has been considered, which is excited by dynamic loading. Now, with the background, whatever we have gathered from our previous discussion, where we were talking about the geofoam infill trench. So now my job is a little bit clear, or the little bit say easier to make you understand about the bamboo infill trench. The concept and all those things are remaining same. Only thing is that inside the trench we are putting bamboo in place of geofoam. Okay, and here we are using square foundation. So therefore the problem becomes three-dimensional problem. So this is the problem. So you have the square footing here. So D, small d is the distance or the spacing between the footing and the trench. Small L is the length of the trench, because earlier in case of geofoam, we didn't have the length of the trench as one of the parameter, because at that time we were talking about either plane strain or axisymmetry, so length was not coming into the picture. But here length is one of the parameters. Okay, now this is on the plan view. So now you have trench on both the sides. Okay, and the trench is filled with bamboo. You can see that. Now here this is a cross-sectional view. So this is the trench filled with bamboo. Small h is the depth of trench, and d is the spacing or the location or the distance between the trench and the foundation or the source. So this is the influence domain with boundary conditions. So we have used infinite elements, because now this is not exactly the same problem whatever we considered for geofoam. There we used absorbent boundary, Lisma-Coulemer absorbent boundary. But here this is the three-dimensional problem, and we considered infinite elements, and we saw that these infinite elements were giving better say response. Now why we use that infinite elements? Because we don't want any unnecessarily waves which will be getting reflected back to the domain again. These are all numerical technique issues. I am not going to discuss that thing here at this moment, because unnecessarily you will be losing interest on the physics of the problem. Anyway, so so this is the trench. This is the source. Okay, where we are putting the dynamic load, dynamic excitation, and the domain size again was selected based on the sensitivity analysis as we did earlier. This is the nomenclature is adapted here. DIHJLKGM. So D stands for location factor. So it is a bit different than the previous one. Don't get confused from both the parameters. Here D is location factor, because L here is used for length factor. Okay. So D is location factor. Capital H is depth factor. L is length factor, and G is the gap factor. Now here also we use intermittent bamboo infill. That means alternate arrangement of bamboo and air pocket. One bamboo, then air pocket, then one bamboo, two bamboo diameter air pocket, something like that. Okay, so gap factor. So that will create the intermittent geofoam. If G is 0, that means there is no gap, continuous bamboo infill trench. If G is 1, that means we are leaving one bamboo diameter in between, okay, as air pocket. If G is 2, then that means we are keeping two bamboo diameter as a void space, and then we are putting alternate bamboo. Now coming to the response. So this is the variation of ARF, the same definition with x by lambda r. X means horizontal distance from the source, okay, for different L. What is L? L is the length factor, right? So now you see other things are remaining constant. D is 0.2, H is 1, G is 0. That means we are considering continuous bamboo infill trench. Now L is 2.8, 3.2 and 3.6. Now here you see as your L increases, that means as your length of the trench increases, you are getting better efficiency. That means ARF decreases, right? ARF decreases means you are getting better screening efficiency. That you are observing here. So without, when L is 2.8, you are getting the ARF distribution here. When L becomes 3.6, you are getting ARF distribution here. Okay. Now you may ask me, I can go for infinite length of trench, but that is not feasible. Somehow we have to stop. Now where to stop? You will continuously, if you change the L value, you will see that later on you will not be getting much difference in the response. So therefore, somewhere you have to optimize. So that thing you have to take your own judgment. Now this is the variation for different D. Where is D? What is D? D is the distance factor, right? The location factor. So here you can see as your D increases, your ARF increases. That means your screening efficiency decreases. So that means, that is quite obvious. Already we have seen that thing in the geoform as well. That means your trench should be as close as possible of the source. Now coming to the variation of ARF with different H. H is nothing but the depth of trench. So here you can see as H increases from 0.8 to 1.2, ARF decreases, okay, significantly. And then you can ask me then up to what depth should I go? So that you have to find out from the optimization study. So, and you go on increase the depth, you will see at somewhere you will not be getting much difference. So you have to stop. And at the same time, you have to see the feasibility. You cannot go for 20-meter depth of trench. It is not feasible. So that should be restricted. So, and another thing is that, see, generally Woods has proposed that this ARF should be 0.25 for any kind of, say, suppose if you want to protect your house or protect any structure from the unwanted vibration, ARF limit should be 0.25. Okay, so here the 0.25 is here, suppose, for example. Now, for further depth, you can come up to 0.25. We didn't go for that because the analysis itself was taking too much of time. So anyway, but the thing is that if you select your benchmark ARF is 0.25, then based on that you choose your depth, length, or whatever geometric parameters you have in your mind. Now this is the variation of ARF for different G. What is G? As I told you, G is the gap. Now you see here, this is the interesting thing. G0 means continuous bamboo infill trench. There is no gap at all in between the bamboos. And this is the open trench. Now you see open trench is the bottommost line, which is quite obvious because that will be the lowest possible ARF distribution. Okay. And G is 0 means continuous bamboo infill trench. So that is on the top. Right? So this is the maximum possible for this bamboo infill trench. Now in between that, this G1 means I am taking out one bamboo in between. Okay, so one bamboo, then one bamboo diameter is the void space, then another bamboo I am putting, then another bamboo diameter is the void space, so on. That is called G1. Now you see, just by removing one bamboo between two bamboos, you are getting the ARF distribution from here to here. So this much of significant variation you are observing. Okay, just by removing one bamboo. Now, just by removing one bamboo, what are the things you are achieving? You are achieving very high screening efficiency. That is your actual target or the objective. Okay, and at the same time, you are saving the material. Though bamboo is cheaply available, but that is one material, right? So if you save the material, anyway, it will save your money or save your pocket, right? So by removing one bamboo, that means if you go for intermittent intermittent bamboo infill trench, by removing one bamboo, this much of drastical change you are observing. Now by removing two bamboos, that means one bamboo, then two bamboo diameter is a gap, then another bamboo, then two diameter of gap, then another bamboo, something like that. You are achieving the ARF distribution which is lying here. Now you see from G1 to G2 you are not getting that much or the significant difference. What you have observed from G0 to G1, right? So now how many bamboos you will be removing or how you will be configuring your intermittent bamboo infill trench, so that you have to take your decision. You have to judge the situation. Okay. Now you see, by another thing is that by increasing G, that means you 0 to 1, 1 to 2, you are approaching towards the open trench. But achieving open trench is impossible. Okay, why? Because you are using infill trench. You can go very close to open trench, but you cannot achieve it. It is very difficult. Okay, now you can say I'm one bamboo and then I am leaving say 2 meter or 3 meter gap and then another bamboo. Then that is not called infill trench, isn't it? That is as good as open trench. Then you will be getting the response like this, but that is not the target. Target is that you have to give the support to the trench. The trench should not collapse. One bamboo and then 2 meter gap, then another bamboo, the trench will collapse. Okay, so that is not our target. Now coming to the variation of system effectiveness, another new parameter we are going to define here with F, with frequency. Now what is system effectiveness? System effectiveness can be defined as in percentage 1 minus ARF bar into 100. What is ARF bar? ARF bar is the average magnitude of amplitude reduction factor over the horizontal distance x behind the trench and can be expressed as ARF bar, that is equal to 1 by x integration ARF dx. That means, I mean, in one word, if I want to explain this, without going to the mathematical expression. So suppose you have the pickup points just behind the trench. Okay, so at each pickup point you just take the response, you capture the response. Okay, ARF response, and then those ARF, the average of those ARF, okay, along at all pickup points is your ARF bar. Now 1 minus ARF bar your system effectiveness. That means it will give you the idea that how much effective is your system. Your system effectiveness should be as high as possible. That is your target that you want to achieve. If it is increasing, that means you are getting better efficiency, better screening system. Okay, now you see here, when F is 50 Hz, at that time your system effectiveness is around 57 kind of thing. If you increase your frequency at 60 Hz, at that time your system effectiveness is going up to say 65 point something like that. And again, if you go for 70 Hz, so these are frequency excitation, okay, machine excitation, right? So when you are going to 70 Hz, you are almost 68% system effectiveness. What conclusion you can draw from this? Yes. Hello.
Yes, sir. Yes, sir. You please carry on. I think there was some sort of.
Okay, I heard some noise. Any question?
No question, sir. You please carry on.
Okay. So now this is for D equal to 1 meter. So D is the distance between the source and the trench. H is the depth, that is 5 meter. L, small l, that is 16 meter, that is the length of the trench, and G is 0, that is continuous continuous bamboo infill trench. Now you see the main or the important observation what we can get from this figure, that as you increase your machine excitation or the frequency of the machine excitation, that means from 50 Hz to 70 Hz, if you go, your effectiveness, system effectiveness or the efficiency is going from 57 to 68%. So that means this kind of technology or this kind of say concept is very, very effective for high frequency machines. That was same observation in case of geoform. We observed that. Here also we observed the same thing. Okay, so this will give you the idea that when you will be choosing this kind of screening system, vibration screening system. Now coming to the summary for this part of work, a substantial enhancement in system effectiveness can be accomplished by considering the intermittent bamboo infill trench over the continuous bamboo infill trench. Okay. However, the value of system effectiveness is found to be maximum for the open trench for the obvious reason that I told you. Open trench will give you the maximum efficiency or the maximum system effectiveness. However, the intermittent bamboo infill trench will give you better than CF. Okay. Now for the continuous bamboo infill trench, the critical parameters are seen to be location, depth and length of the trench. Whereas for the intermittent bamboo infill trench, the spacing between the bamboos plays a bamboo infill trench, the spacing between the bamboos plays a crucial factor in. Now the intermittent bamboo infill trench with H equal to 1.2, L equal to 3.6 and D equal to 0.2 and G equal to 2 is found to be the most efficient from the viewpoint of screening and cost effectiveness. As I mean, it might come to your mind that what could be the optimum configuration. It may or may not be same whatever I am proposing. However, you have to, I mean, for these are all very case specific, site specific, location specific. However, from this study, what we can draw that H, that is the H factor, that is depth factor is 1.2, and L is nothing but your location factor. Length factor, that is 3.6, and D is the location factor, that is 0.2, and G is 2. Okay, G is 2 is fair enough. Okay, for getting the optimum efficiency. The system effectiveness of BIT is found to increase with the increase in the frequency of the vibrating source, as we have observed, and hence BIT is expected to be more efficient for high frequency vibrating sources such as compressors, high speed turbines, generators, etc. Okay, so if you are dealing with the vibration coming from these machines, so I mean blindly don't apply the technology everywhere. Okay, so if you have very low frequency machines and if you want to arrest or if you want to screen the vibration coming from those low frequency machines, this technology or this concept may not be very effective, but high frequency machines, it will be effective. So these are the things you need to take the judgment. So whatever solutions available in the community. So my suggestion is, or my request is that don't go blindly. I mean, you think about the limitations, you think about the conclusions. Then only you can apply those technologies for the betterment of the people. Okay. So I acknowledge these works are done. I mean, the first part, that is geoform part, was done by Mr. Mainak Majumdar, former research scholar. So now he is doctor, of course. And Mr. Rajiv Kumar, he was my former AICTE student. Thank you very much. So this is our nice and beautiful campus. So I'll be happy to answer your questions if you have it.
Thank you very much, Professor Ghosh, for making us understand, learn this interesting topic of area of research. And if any participant is having any question, I think they can raise. I think one of Yeah, Mr. Sridhara, you can ask your question. Let me just unmute you. Yeah, please go ahead.
Okay, right. Got it. Thank you. Am I audible?
Yeah, you're perfectly audible.
Yes. Thank you, Professor Ghosh, sir. We are blessed to listen to you. The frequency with which actually you are actually presenting your findings is really as if I am actually thinking of sitting in a classroom as a student. Thank you so much for the frequency with which actually you are transferring the data. I have two questions. First one, in case of geoforms, okay, one thing is the excitation is from the machines having this sinusoidal excitation. And considering the ground motion, sir, coming from the other side, because of some vibration. Can we relate, maybe reasonably will be avoided because you have started with base isolation, then we have moved on to screening. Okay, this screening, how effective this screening will be for ground motions, like maybe traffic or maybe earthquake motions? That's my first question. Thank you.
Okay. Thank you for the question, Mr. Sridhar. So actually, in this whole talk and in this whole study, actually, we have studied only the active screening system. Okay. However, for screening, people have used geoform infill range like blast loading. Blast loading is a kind of passive screening. So blast source is somewhere else, and you want to protect your structure which is far away from the source. So people have used. It is not like that it can be only used for the active screening. It can be used for the passive screening as well. But for the earthquake, I am not pretty sure, because it has got, because earthquake is having the summation of different frequencies, right? So some frequencies will be screened effectively, some frequencies will not be screened, and moreover, the trench, whatever I am talking about, the trench should exist in case of earthquake. So in earthquake, if the trench itself doesn't exist, then basically there is no point of having the screening, question of screening. So that is the important thing. So if considering this issue, okay, even in the earthquake situation, even the trench is stable and everything remains same. Only thing is that, and trench is acting as a screening system, then I will say that the effectiveness of the screening system may not be that good, because it will be having the mixed frequency in the earthquake excitation. Okay. Starting from very, very high frequency, it will be screened properly, but low frequency it will not be. But in case of machine or other things, what you see that you have a monotonous kind of frequency. Either the machine is running for 10 Hz or 20 Hz or 50 Hz, so you can plan properly. But in case of earthquake, it is difficult to plan. And at this time, at this point of time, what I should say that nobody has used this kind of screening system in case of earthquake. I'm telling you.
Yes.
The open trench and this infill kind of thing, because we don't know or will not be knowing the fate of the trench itself during the earthquake. That is one thing. Another thing is that if suppose the whole structure is gone,
yes,
and it is not like that the whole structure you are basically isolating. That's why I told you initially that I am not using the word isolation for this. I am screening. Some amount of vibration always will be going there. Okay, but in case of isolation, what it does, it completely isolates the system from the rest of the world, isn't it? So that is not served by this technology.
Thank you, sir. We can use it in a combined form, no, sir. Just screening can be used as
yes. So you can reduce. I mean, state-wise. So maybe one trench is not sufficient. Multiple trench people have used. Multiple trench. Sometimes one trench is not sufficient. So people have got for one trench, then another trench, then another trench, and something like that.
Because most of the time our structure will be stiffer, so that we will be having a high frequency in the structure, but we are moving into the displacement side by giving this damping equipment, just to go to this displacement dominated mode. That's the reason. Sir, thank you so much. For second question, in case of bamboo, sir, when we are actually removing one bamboo, we are actually getting a very low ARF, as you said. When we are actually removing one bamboo in between, we are actually, I like to know the stability when we remove that bamboo in between, stability of the sides.
Okay. The stability will be achieved by properly designing the panel. As I was showing about the geofoam panel, so if I say the panel means top cover, then bamboo, then the bottom cover. Now this top cover and bottom cover, the side covers basically, this side cover should be strong enough. Now here in the experiment, what we are using plywood. Instead of plywood, you can use PVC stiffened by some geosynthetic geonet or maybe a steel net or whatever. Now in between these two panels, you will be putting the bamboos. Now, if you look at our local bamboos, you will not be getting that much diameter. But I am telling you, if you go to Northeast or if you go to Japan or any South Asian countries, you will see the bamboo size is too big. I mean, it is a kind of your wood log or kind of that kind of thing. So the diameter is very high. So in that way, you will be getting very good, gap in between two bamboos. That is one thing. Second thing I forgot to tell you during the talk, that yes, bamboo is not, bamboo is biodegradable, right? After a certain time, I mean, if it is seasoned bamboo or if it is, some kind of treatment, you have treated bamboo, if you use, maybe 6 years or 7 years you can put. But the same thing, again, you will be putting that thing in the panel, the whole panel can be lifted up, you remove the side cover, you replace with the fresh bamboo, and then again you can refill that thing in the trench. So that kind of arrangement or that kind of installation process can be achieved. So the bamboo diameter, now how many bamboos you will be leaving and whether your panel will be stable or not, that you have to do the analysis before inserting or before installing the panel.
Thank you so much, sir. Blessed to listen to you. Thank you.
Yeah, you're welcome.
Yeah. Any other question from any participant? I think we had a wonderful discussion also. Sir, I had one question regarding whether this kind of technology, I think it's still at the laboratory level, but still whether it has been somewhere installed in the world, like are they thinking into on these same lines?
No, geofoam infill trench has been installed. It has been installed in the world. I am not pretty sure about India, but outside India, it has been installed. In Germany, people have used a lot. In European countries, people have used a lot geofoam infill or gas and all those things. Infill trench has been used. But this bamboo is completely new. I mean, frankly speaking, we tried it first time, and then again, we are also novice because we are also working on the field to do some field experiment. And then once the field experiment is over, then we can say at least, because numerically you will see, you will be able to see the one side of the coin, right? Another side of the coin will be more clear when you will be doing some experiment. And then the whole coin will be visible to us. So right now we are working on the field experiment. Then it will be more clear to us that how it can be installed and what are the troubles involved in the installation process. And during the experiment, what are the problems or what are the things we are going to achieve. So that we are working. So this bamboo infill trench, nobody has used, never it was used. Okay, so far. But geofoam infill, yes, people have used.
Okay, thank you, sir. I think next lecture will be we are hoping that where you will be showing us more of a field study.
Sure.
Yeah, that will be so that two phases of the coin are definitely visible to all of us.
Yeah, by this time I could have shown something, but because of this pandemic, that experiment completely got stopped for last 2 years.
Yeah, but this sounds something very noble also.
Yeah,
I think, sir, I think definitely you might have kept in mind about the patent also, because this kind of idea, you know, because the similar sort of idea, if you remember, that was there in the helical soil nilling also.
Yeah.
So I think we expect a patent also out of it from your side.
Yeah. So actually, sometimes what is happening, I mean, you have to see the material in a broader perspective, right? I mean, this insight. I mean, if you know the physics of the problem, then rest of the things will come out automatically. So you need to capture the physics. So that's what we thought initially. The bamboo. I mean, people are also reluctant. I mean, how the bamboo can give the isolation for the screening. So then we tried with numerical things. With that, if we get some encouraging results, then we'll go to field, and that we are doing now.
Right, sir. Right. Thank you very much, sir. Thank you once again. And next time, we hope that there will be no pandemic, and we can host you in the beautiful hills of Shimla.
Yeah. Thank you. I am also eager to see that. Yeah.
Yeah. Thank you. Thank you very much, sir. Thank you.
Yeah. You're welcome.
Yeah. So
thanks to all. And, And I mean, if somebody is not asking the question right now, or if they want to ask the question, they can send me mail. No problem.
Yeah, as suggested, so you can also send an email to him regarding query related to this topic, and I think he will love to reply to your queries. So with these words, I thank him again for taking out time of 2 hours. Initially, we thought that it will be 1 hour, but then AICTE told us it has to be for 2 hours. So thank you very much, sir, and thank you to all the participants. Tomorrow we'll start our next session from 10 a.m. Professor Dipankar Chaudhary from IIT Bombay will be joining us for the first session. So I request all of you to join us at 10 a.m. tomorrow, Tuesday. Thank you very much. For any query, for any other thing, you can always send your query on WhatsApp group. You can text, you can call me, you can mail me. Yeah. So for tomorrow, as I told you, that we'll have tomorrow 4 speakers, as also shown on this slide here. So Professor Dipankar Chaudhary, along with Dr. Ashutosh Kumar, will be speaking on earthquake resilient in foundation system. And then Dr. K.V. Uday will be delivering a wonderful, exciting lecture regarding landslide disaster risk reduction. So he's having wonderful things to showcase to all of us. And then at last, Dr. Aninde Pine will be there from CSIR CBRI Roorkee. So with these words, I thank all of you again, and we will meet tomorrow at 10 a.m. So please be there before 10 a.m. because our speaker is very much busy professor. He's taking out time especially to deliver a lecture. So I request again that all of you will be there by 10 a.m. Thank you. Thank you very much. And I think one of the participants, Mr. Ravindra, is saying, please send feedback link. I think, sir, we have already sent you the feedback link. You please check this chat box. It is there already. Okay. Thank you, Sridhara, sir. Thank you very much. My anchoring has to go for next 4 days also. Thank you. Again, I think my team has again posted it here. So, yeah. So all the participants need to fill this feedback form. Okay. So we need to, I think, submit it to AICTE also. And at last, I would again like to tell you, all of you, is that you are only eligible for certificates if your attendance is more than 80% and you are scoring in your quiz more than 60%. So these are the 2 guidelines given by AICTE. I request all of you to please keep those 2 things in your mind. With these words, I thank all of you for joining all the sessions of today. and let us meet tomorrow before 10 a.m. Thank you very much.